It's finally time. After so many brief histories of so many momentous events and people in spaceflight history, we arrive, finally, at a brief history of the Space Shuttle program. For 30 years, from 1981 all the way until 2011, the Space Shuttle was the first attempt at reusability in spaceflight history, and you'll see why I say attempt in a moment. It was innovative, it was absurdly intricate, it was unprecedented, and it has yet to be matched in capability, but it was also crippled from the outset, deeply flawed, and remains the most dangerous space vehicle to have ever flown to date. It is a complicated legacy, and a long one, so strap in, buckle up, face forward, and feel the twang. Like so very many subjects, we have to begin at Project Apollo. Long before the very first lunar landing had ever occurred, people were already considering what would come next for the National Aeronautics and Space Administration. Despite all of the effort and funding and work that had gone into Apollo, many people at the top realized it wasn't going to last. It was a project fueled by politics, and once somebody won the race, the politics weren't going to pay the bills anymore. Before the first US flag was flying on the moon, the process of dismantling the infrastructure of Apollo had already begun. While the minds behind the program were scrambling to try and salvage what little they could of what they had built, the powers that be were discussing what should come next for human space exploration. Just a few months after Apollo 11 landed, the Space Task Group submitted a report titled The Post-Apollo Space Program: Directions for the Future in September of 1969. The report detailed the important national resources found within the burgeoning space program, stating that the broad foundation that allowed for the success of Apollo provided a wide array of new and challenging opportunities for the future. It concluded that the United States should seize these new opportunities to, quote, advance science and engineering, international relations, and enhance the prospects for peace, while also acknowledging that national priorities of the time existed in contrast to the high cost of the manned space program. Think Vietnam War and Civil Rights Movement. It also acknowledged that NASA had demonstrated the competence and technology base to carry out a manned Mars mission within 15 years, and this part would become one of the bases of the 4 recommendations given by Spiro Agnew's council in that same year. The 4 major options that were considered were 1. A human mission to Mars, 2. A follow-on lunar program, 3. A low Earth orbital infrastructure program, and 4. Discontinuing human spaceflight activities altogether. Think about that for a moment. Just 3 months after mankind had used its own hands to plant a flag on a celestial body 250,000 miles away from the Earth, one of the options considered was throwing in the towel completely. One day I'll make a video about how learning about space history has left me with a massive case of cosmic depression. Anyway, they chose the third option. More specifically, President Nixon, acting on the advice of the Council, chose the orbital infrastructure option. There were several parts to this: the construction of a space station, development of a space shuttle, and research on methods and technology to facilitate longer-term missions, eventually making a human mission to Mars much more feasible. Bear in mind that Mars is monumentally further away and more difficult to get to than the Moon. This infrastructure program would form the basis of what was initially called the Integrated Program Plan. The IPP consisted of several parts, only a few of which would end up in the final program. One was the Earth-to-Orbit shuttle, intended for low-mass, high-frequency payloads, having a quick turnaround between flights to allow for things like crew rotations. Another aspect was a modular space tug designed by the Marshall Space Flight Center. It would have a basic propulsions module, and could have either a payload module or a crew module attached to it, as well as optional legs for landing payloads on the Moon. A crew module concept included robotic arms that would allow for complex tasks such as on-orbit satellite repair. There was also a nuclear ferry, another modular concept that utilized nuclear thermal engines which would vastly improve payload capacity. These nuclear engines could be used to take payloads from low Earth orbit, which got there either through the shuttle or the space tug, and propel them further to the Moon or even Mars. The nuclear ferry was one aspect of the IPP that actually made it off of paper. The Nuclear Engine for Rocket Vehicle Application or NERVA program ran for nearly 2 decades, beginning as early as 1953 when physicist Robert Bussard wrote a study on nuclear energy for rocket propulsion. It took some time for his work to gain attention, but by 1957, a test site began construction in Jackass Flats, Nevada under the name Project Rover. Once the space race began after the first satellites were launched, control of Project Rover was transferred to the newly formed NASA, and despite being successfully tested in the early 1960s, NERVA was constantly on and off the chopping block. It was heavily defunded by the time of the IPP proposal in the face of the mounting costs of Apollo and the Vietnam War, and would eventually be cancelled entirely in 1973. Outside of the shuttle, the only other concept from the IPP that would survive its infancy was a space station. However, unlike what we would eventually get, the IPP called for multiple space stations built out of standardized modules and placed in several different orbits, from LEO to polar Earth orbit, geostationary orbit, and even an orbit around the Moon. Because the IPP was so focused on paving the way for eventual Mars missions, part of the plan included transferring these station modules onto nuclear ferries and using them as the crew sections for a journey to Mars. After the success of Apollo, the IPP's downfall began almost immediately. Facing steep budget cuts in the face of new economic challenges and waning enthusiasm for spaceflight, Nixon's office anticipated rejection of the Space Task Group's ambitious plans. By 1970, everything except the space shuttle was gutted, and with this came the resignation of Thomas Paine, who had championed the IPP. He was replaced with James Fletcher, who would take charge of what would be publicly known as the Space Transportation System, or STS. It was marketed as a cost-effective space truck that would allow for construction of an eventual space station in the 1980s, though we'll get to that. For now, we have to open another can of worms, which is the design of the space shuttle itself, but I'd like to take one quick aside for a little fun fact. In 1972, Apollo 16, the penultimate moon landing, was underway during April. Charlie Duke and Project Gemini veteran John Young were bouncing around on the moon. In fact, they were in the process of taking this iconic photo of Young's leaping salute when they received some good news from Mission Control.
Okay, Charlie, say when. Here we go. Do it again. One for you. Okay, wait a minute, one more.
This looks like a good time for some good news here. The House passed a space budget yesterday, 277 to 60, which includes a vote for the shuttle.
Wonderful. Wonderful. Tony, again, I'll say it with that salute. I'm proud to be an American. I'll tell you, what a program, and what a place, and what an experience. Yeah, and I'll say it too.
So am I.
The country needs that shuttle mighty bad. You'll see.
At the time, the shuttle still had quite the ambitious design and projected capabilities, prompting Young to express excitement at the secured funding and assuring the world that they would see how important the shuttle would be. 9 full years later, Young would be sitting in the commander's seat of Shuttle Columbia for the very first shuttle flight. George Mueller, a key figure in both projects Gemini and Apollo, was at the head of the initial design for the shuttle. By then, he was a highly respected and trusted figure within NASA, having been responsible for proposing reorganization of Marshall to effectively run the Apollo program and proposing the all-up testing of the Saturn V that streamlined its path to success. His proposed design for the shuttle was a 2-stage, fully reusable system using 2 Delta Wing spacecraft. With development contracts given to North American Rockwell and McDonnell Douglas, the idea was extremely complex, raising doubts about the feasibility of it all very early in the process. Study contracts were given to Grumman, Boeing, Lockheed, and Chrysler in 1971. The idea on the surface sounds simple. A small winged vehicle called the orbiter would be fixed on top of a larger winged vehicle called the booster. Launched vertically like a traditional rocket, the booster, which was basically a fuel tank with wings and engines, would carry the orbiter up to around 50 miles or 80 kilometers and then separate. The orbiter would then use its own engines to complete the ride to orbit, while the booster would turn around and descend through the atmosphere to land on a runway near the launch site. After completing its mission, the orbiter would do the same, deorbiting and coming in for a runway landing. Both stages would feature cockpits and instrumentation to allow for landings, independent fuel tanks, and also called for air-breathing turbofan engines that could allow for control during descent and landing. Problems with this initial design quickly became apparent. First was the problem of mass. An orbiter with the high payload capacity that was called for would need a huge booster to lift it into the upper atmosphere. When it comes to spaceflight, mass is directly tied to cost. The bigger and heavier the booster, the more it will cost to develop and build. The 2 separate propulsion modes, jet engines as well as rocket engines, further brought the cost and complexity up. At this time, it wasn't entirely clear how much funding was going to be available for the shuttle program, but it was almost definite that it would be aiming for a lower cost than the Apollo program's whopping $25 billion over 13 years. Those within NASA who were big backers of the shuttle program tried to downplay the cost by noting that reusability cuts down on a higher initial cost over time. If it cost the same to build one shuttle as it did to build 3 Saturn V's, the shuttle would eventually be cheaper as long as it was able to launch more than 3 times, and the initial hope had been for 55 shuttle launches per year in some theoretical studies. It would never reach that point, in fact, would never have been able to, but we'll come back to that. Seeing the potential problems and difficulties of the ambitious Phase A shuttle design studies, designer of the Mercury and Gemini spacecrafts Maxime Fazet stepped up with a new idea. He noted that one of the primary complications of the design was the delta wings, which are blended together with the fuselage. This meant that every time any aspect of the design changed, it changed the weight and balance, which would then in turn require changes to the entire structure of the orbiter. He presented the DC-3, which used a much more conventional layout similar to a normal airplane. It had an almost cylindrical fuselage and low-mounted swept wings. Keeping the wings separate from the body of the craft allowed for changes in weight and balance to be addressed by simply moving or reshaping the wing, much as is done when designing a traditional airplane. The side effect of these separate wings is that the DC-3 would have very little lifting capabilities. During re-entry, achieved at a very alarming 60-degree nose-high angle, the wings would provide practically no aerodynamic benefits. This limited its cross range to be around 300 miles or 482 kilometers, meaning it had very little ability to correct its descent path during re-entry. To compensate for this, the spacecraft would pitch over in the lower atmosphere, open air intake ducts, and start up jet engines to perform a powered flight to the runway, much as was proposed in the Phase A design. Fazet was a respected name within NASA at this point, and his proposal quickly received a lot of support from the Marshall Space Flight Center. It would go up against a rapidly developing logjam of various design concepts from other departments, including recoverable versions of Saturn V boosters, HL-10-inspired lifting bodies from Langley Research Center and Dryden Flight Research Center, and even an incredibly ambitious proposal for a single stage-to-orbit spaceplane. By January of 1970, NASA had consolidated all of the proposals and dropped all but 2, the traditional delta wing design and Fazet's DC-3. Reviews of the developing shuttle program were favorable, indicating eventual lower per-launch costs once the reusability aspect became proven. These reports made the shuttle a constant topic of discussion within the federal government, but James Fletcher was still worried about the possibility of the program getting axed. It wasn't an unfounded fear. The shuttle itself was already the result of gutting the entire Apollo applications program down to a singular project, which then itself was cut down to a single vehicle from a proposal of several. He made a decision that was intended to make the shuttle effectively unkillable, but would wind up crippling the entire finalized design. He directed NASA to develop the shuttle to support Air Force requirements, who were then developing a new series of large spy satellites. They were 60 feet or 18.2 meters long, 40,000 pounds or 18,100 kilograms, and would need to be launched into a polar orbit, allowing them to survey all latitudes of the Earth as it rotated beneath them. This was more or less doable, but the Air Force had another requirement that would doom the 2 fully reusable designs. The Air Force wanted the shuttle to be able to do what's called a once-around, go up, perform its mission, and then land again at the end of a singular orbit, making a roughly 90-minute flight. There was a reason for such a quick flight, but at the time it wasn't exactly made public. The plan was for the shuttle to go up with an empty payload bay, and then land again with a full bay, carrying a payload that was not necessarily NASA's property, if you catch my drift. The problem with this mission profile was that the Kennedy Space Center would rotate about 1,350 miles or 2,170 kilometers over the course of a single orbit. The vehicle would then need at least this amount of cross-range capability during re-entry, though the set requirement was 1,500 miles just in case. DC-3, with its simplistic and ballistic re-entry profile, simply could not achieve this. At this point, Fazet's design was permanently shelved. Furthermore, the base design was capable of carrying a 25,000 pound or 11,300 kilogram payload to orbit, about 15,000 pounds or 6,800 kilograms shy of the new spy satellites. This new design was a compromise, partial reusability instead of full. The initial design had the orbiter carrying its own liquid propellant, and this in turn was one of the limits of its payload capacity. The solution was simple: move the fuel outside of the orbiter and carry it in an external tank that would be discarded after use. Though it removed reusability, this was seen as acceptable due to the tank being the cheapest component to produce, about $78 million a pop. This would also effectively handicap the flight rate. The initial 55 launches per year became impossible as the McCoud assembly facility was only capable of producing 24 tanks per year. Seeking to further increase payload capacity and decrease cost and complexity, the next component to be discarded was jet engines. NASA already had experience with vehicles that went up with rockets and came down with glide capabilities, namely the X-15. In addition, the size of the crew was up for debate. Some stated the shuttle shouldn't need a larger crew than 4, a commander, a pilot, a mission specialist, and a payload specialist. This was also the limit of how many seats could be fitted with ejection seats, but NASA expected to carry more payload specialists on future missions, especially when it came to assembly of what was yet to be named the International Space Station. In the end, the orbiter was designed for a crew of up to 8, 4 on the flight deck and 3 to 4 on the middeck below. The final component up for debate was the boosters. There were 4 options to be considered. One was to use the first stage of the Saturn V, the S-1C, mounted beneath the external tank. Another was to develop a similar but newly designed stage of simple pressure-fed engines, and another was to use a large singular solid rocket booster. The fourth was the option that would end up being used, 2 smaller solid rocket boosters mounted on the sides of the external tank. There was briefly a discussion about whether these boosters should be solid or liquid-fueled. While solids are relatively cheap, simple, and powerful, liquid fuel is more reliable and was seen as safer due to its abilities for control. Liquid-fueled engines can be easily throttled or shut down entirely mid-flight in the case of an emergency. Furthermore, they provide better fuel efficiency and more uniform thrust, but in the end the cost argument won out, resulting in the design to use solid rocket boosters, though not without concerns being expressed. One drawback of a solid booster is that it cannot be throttled or shut down. Like a firework, once it's been lit, it will simply burn at maximum output until the propellant runs out. This created black zones in the shuttle's abort options, which we'll cover later, and many were concerned about whether or not an ejection from the shuttle orbiter would even be possible while those boosters were firing. Response to these concerns from test pilots were very, let's say, direct.
It's still not completely clear to me whether or not you can abort with the ejection seats during the burn of the solids.
You just pulled a little handle.
All of the plans were now in place. The basic finalized shuttle design that we know was cemented as early as 1972, as we can see in this image of Richard Nixon being shown a model by James Fletcher. A very similar model can be seen at KSC in this image, with the Saturn V rocket for Apollo 16 in the background, in April of 1972. In this year, Lockheed, Douglas, Grumman, and North American Rockwell submitted proposals to build the shuttle. The first 3 were deemed too expensive, with Lockheed being cited for their lack of experience with crewed spacecraft at that time, and North American was chosen in July of 1972. At the same time, Vandenberg Space Launch Complex 6, left unfinished when the Manned Orbital Laboratory project was cancelled, resumed construction with extensive modifications for shuttle operations, including changes to the mobile service tower, new flame ducts, liquid hydrogen and liquid oxygen storage tanks, a payload preparation room, and more. Now, before we go any further, the final design of the shuttle stack has been established, so let's go over exactly what that was. The shuttle consisted of 3 primary components: the spaceplane, called the orbiter, the external fuel tank, and the twin solid rocket boosters. The boosters, the first solids to ever be used on a crewed launch system, were manufactured by Thiokol, later purchased by ATK, consisting of 4 segments that together stood approximately 149 feet or 45.46 meters tall, with a diameter of 12.17 feet or 3.71 meters. Each booster weighed 1.3 million pounds or 590 tons when full of fuel. Their powerful 3.3 million pounds of thrust provided around 80% of the shuttle's total thrust at liftoff, carrying the vehicle through the first 2 minutes of the flight. At an altitude of around 45 kilometers, they would then be jettisoned via explosive bolts and pushed away from the stack with small separation motors. After descending back toward the water, the nose cap would blow away and a pilot parachute would be deployed from within the top of the booster, which in turn pulls out a drogue parachute. Now properly oriented tail first, the main chutes deploy, and just before splashdown, the nozzle extension is separated, designed to be lightweight and expendable, and the rest of the booster would then splash down into the water to be recovered and refurbished for reuse. A fun note about these boosters: due to their massive size, they couldn't be shipped whole, and were instead transported on heavy-duty rail cars in the 4 main segments, aside from the nose cone and the aft skirt. The rail route went from Utah to Florida, passing through multiple mountainous regions with tunnels and bridges. U.S. railroads have a standard track size that restricts cargo to 10 feet and 8 inches in diameter. The SRB segments at 12 feet in diameter would require special permits, routing, and sometimes even temporary track modifications, stretching the upper limit of what those routes could possibly handle for cargo. In fact, NASA engineers ended up limiting the diameter of the final SRB design specifically because of these railroad routes. They had wanted to increase the diameter for better performance, but the cost of logistics challenges in moving them around was simply too high. In a way, These railroad tracks became the reason that the boosters were the size that they were. The external fuel tank, or ET, manufactured by Martin Marietta and later Lockheed Martin, was the physically largest component of the stack, standing 153 feet or 46.9 meters tall with a 27.6 foot or 8.4 meter diameter, and was the only component that was fully discarded after launch. In addition to holding the liquid hydrogen and liquid oxygen tank, the ET served as the backbone of the stack, providing the attach point for both boosters and the orbiter. Between the hydrogen tank at the base and the LOX tank at the top was an intertank, which served as a compartment to house several electrical components to allow for communication between the ET, the boosters, and the orbiter during launch. The ET was coated with spray-on foam insulation, or SOFI, as well as several pieces of preformed foam and ablator materials, the exact details of which would evolve over the course of the program due to ongoing problems with pieces of foam breaking off during launch. We'll definitely come back to that. For the first 2 test flights, the ET was painted white to help regulate its temperature while it waited on the launch pad. However, not only was this found to be unnecessary, but removing the paint would save nearly 600 pounds of weight from the stack. The most complex component of the shuttle stack was, obviously, the orbiter, built by Rockwell International. In the end, 5 space-worthy orbiters would be built: Columbia, Challenger, Discovery, Atlantis, and Endeavour. Each would have slight differences between them, but we'll go through those differences in more detail as we go on. Generally speaking, they were 122 feet or 37.23 meters long, 58 feet or 17.86 meters tall, and had a wingspan of 78 feet or 23.79 meters. With a structure of aluminum alloy, the outside of the orbiter was covered with white ceramic tiles made of high-purity silica fibers, with some areas instead having quilted blankets rather than individual tiles, made of a replaceable mix of insulated materials. These were used to protect from both the extreme cold of space and the extreme heat of re-entry. To further protect from re-entry, a complex system of over 30,000 black tiles covered the bottom of the craft, which was oriented toward the airflow during the re-entry process. Its landing gear, with 2 main gears and 1 forward, could only be lowered by manual controls. This was because, due to them lowering through doors in the heat shield, an accidental deployment by a computer could be catastrophic if it occurred during launch or in space. The gear focused on being extremely reliable, using triple redundant hydraulics and even pyrotechnic charges as a backup. Since the shuttle landed at high speeds and only had 1 shot to get it right, it was imperative that a belly landing never ever occur. It would likely be fatal for both the vehicle and the occupants. While in space, the orbiter utilized 2 sets of reaction control thrusters at the nose end and at the aft to orient itself. These used hydrazine and dinitrogen tetroxide for fuel, sharing with the orbital maneuvering system engines, which could be used to change the vehicle's orbital path. This kind of fuel is particularly effective in space, igniting on contact with each other and allowing for easy restarts without a separate ignition source. The reaction control system could also assist in orienting the vehicle during re-entry until the denser air is reached and the lifting surfaces become effective again. The orbiter's pressurized cabin had 2 floors. On top was the flight deck, essentially the cockpit. Containing over 2,000 individual controls and displays, the flight deck held 2 permanent seats for the commander and pilot, with 2 more stowable seats for mission specialists. One of these seats was located behind and between the front 2, allowing that mission specialist to serve as a flight engineer during the launch and landing, tracking information, communicating with Capcom, and calling out milestones. At the back of the flight deck were 4 windows, 2 looking into the payload bay and 2 looking above the cabin, as well as a host of other controls, primarily dedicated to robotics and payload bay systems. Below the flight deck is the mid-deck, with 2 to 4 more stowable seats, though only 1 flight ever used the 4th seat, as well as the galley, toilet, spaces for storage and sleeping, and the side hatch, which you can see here from the outside. At the back was the airlock, with a hatch on the other side leading to the payload bay for the purpose of spacewalks. Now, how did the shuttle produce electrical power? Generally, an airplane in the atmosphere gets power from generators in its jet engines, as well as auxiliary power units. Instead, the shuttle used a set of 3 hydrogen-oxygen fuel cells powering the entire stack through the launch process, as well as to the orbiter's various systems in orbit. Located beneath the payload bay liner near the front of the fuselage, they provided around 21 kilowatts of power, 14 of which were used by the orbiter, with 7 reserved for whatever payload it was carrying. These fuel cells also provided power for the flight computers, 5 identical IBM AP101 avionics computers with their own specialized programming language. All 5 controlled the onboard systems at once, so that if any were to fail, and sometimes they would, there would be no lapse in control. The largest section of the orbiter, the payload bay, was 60 feet or 18.3 meters long and 15 feet or 4.6 meters wide, just long enough to fit those spy satellites we talked about earlier. Shuttle Columbia's payload bay was very slightly longer, as it was never equipped with a docking mechanism, which came into play on at least one occasion, which we'll get to. Its two doors would open shortly after reaching orbit and remain so for the majority of the flight due to the inside of the doors holding the deployable and fixed radiator systems for heat rejection. Capable of carrying 55,000 pounds or 25,000 kilograms of payloads to low orbit, it included various tie-down fittings, hinges, and structural supports for holding the payloads, some of which were modular and could be removed or added depending on the requirements of the mission. Some payloads were even specifically designed to be held by the shuttle with its cylindrical bay kept in mind, including the tracking and data relay satellites and the Hubble Space Telescope. At the rear of the orbiter was one of the most important components, the three Space Shuttle Main Engines or SSMEs, otherwise known as the Rocketdyne RS-25 engines. There's a lot that could be said about these engines. They were some of the most complicated engines of their time, working in a highly efficient staged combustion cycle for high fuel efficiency. The fuels were partially burned in two pre-burners first, fed through turbopumps, then fully combusted in the main chamber to produce thrust. These rings you see on the outside of the nozzle are for regenerative cooling. Liquid hydrogen is cryogenic, requiring it to be stored at very low temperatures, and thus the nozzle is kept cool during firing by feeding the hydrogen through the tubes in these rings before they entered the combustion process. The engines were extremely reliable, only ever experiencing one in-flight shutdown, which we'll get to, and their most notable feature was reusability. Being attached to the orbiter meant that after landing, they could be examined, refurbished if needed, and flown again. The SSME were some of the most advanced of their time. Even their startup sequence is something that boggles the mind. I won't go into it, but here's a short clip from someone a lot smarter than me about it.
And to walk through this, I'm going to cut the speed in half and use this very nice graph I showed you earlier. The main things to watch are the blue line, which is rising right now, that is the main fuel valve, and the dotted magenta line, which has just started rising, that is the main oxidizer valve. So the hydrogen starts flowing into the engine, but the engine is warmer than the boiling point of hydrogen, so it vaporizes. And that, on one hand, helps provide pressure to spin up the turbines, but on the other hand, the back pressure actually causes pressure waves or oscillations in the propellant flow. And these are significant enough for the first second and a half, they actually have to time some of the valve position adjustments to line up with the oscillations.
They would, in fact, be one of the main reasons behind the delay of the Space Shuttle's debut. At one point in its development, there was a plan for the shuttle to reboost the slowly decaying Skylab space station and even potentially service an expansion for it. However, initial testing in the early 1970s suffered constant failures, unveiling shortcomings in the nozzles, valves, preburners, and the main combustion chambers. Full engine tests in 1975 unveiled more problems: weld cracks, housing burn-throughs, coolant liner failures, duct failures, fuel injector blockages, and hot gas pathing. Solving these problems took a long time, pushing the shuttle's debut all the way back until 1981, but the end result was an exceptionally powerful and reliable engine that never failed throughout 135 flights, with one exception. Sort of. Again, we'll get to it. The livery of the Space Shuttle Orbiter fleet, that is, the markings and insignias featured on the outside, would change over time. Originally, the Test Orbiter Enterprise set a standard, with the letters USA on the right wing and an American flag on the left, and the orbiter's name in Helvetica on the side of the fuselage just above the hinges of the payload bay doors. The NASA worm logo was featured just ahead of the OMS pods, and along the side of the fuselage just above the wings were another American flag and the text United States. In 1983, Shuttle Challenger set a new standard for itself, Atlantis, Endeavour, and Discovery, though Columbia retained its old layout. USA was added above the flag on the left wing, while the NASA worm logo with the orbiter name was placed on the right. The name on the fuselage was moved to just below and behind the cockpit windows, making it visible when the payload bay was open. Then in 1998, all four remaining orbiters were refitted, with Columbia brought up to date with the others. The worm logo was phased out entirely, replaced with the meatball logo, and the wing markings were switched around. Now that we've talked about the shuttle itself, let's talk about infrastructure. Let me just check my notes here, and yeah, this is going to be a long one, huh? During the Apollo program, KSC had 3 mobile launcher platforms constructed to facilitate transporting and launching the Saturn V and Saturn 1B rockets. Following Apollo, the bases of the mobile launchers were modified for the shuttle. The tower sections were removed, and portions of these were erected permanently at launch pads 39A and 39B. Additions were made to these towers, including swing arms, electrical connections, and the beanie cap, a gaseous oxygen vent arm to capture liquid oxygen vapor from the top of the external tank. The rotating service structure was added, a massive structure that rotated 120 degrees on a track, enclosing the shuttle for payload installation, servicing, and protection. Flame trench modifications were made to handle the shuttle's asymmetrical exhaust, the sound suppression water system was upgraded, new propellant storage facilities, slide wire escape baskets, lightning masks, and pad terminal connection rooms were added. Two tail service masts were added to the mobile launchers on either side of the main engine's exhaust vent, containing the feed lines for the external tank's fuel as well as electrical hookups and flares that were used to burn off residual hydrogen vapors prior to main engine start. While the main engines would vent their exhaust through the same opening the Saturn rockets did, 2 more exhaust ports needed to be added for the solid rocket boosters. Now, one last thing before we get back to the timeline we were discussing. Let's talk about abort scenarios.
You just pulled a little handle.
Traditionally, up to this point, flights would be aborted with the use of a launch escape tower, a small attachment at the top of a capsule designed to pull it away from a failing rocket and save the crew. An exception is Gemini, which used some pretty questionable ejection seats, but the shuttle didn't have an escape tower. It did have ejection seats for the first 4 test flights, after which their size and structural requirements would have limited crew and payload capacities. From that point forward, they relied on a system of staged abort modes that depended on where, when, and how many failures occurred during ascent. The first possible abort mode took place before liftoff, the Redundant Set Launch Sequencer or RSLS abort. As the shuttle's main engines ignited at around T-6 seconds, flight computers had a moment to monitor their performance as they built up thrust. If any kind of inconsistency was detected, such as a temperature reading being above approved values or low pressure detected in a valve, the engines would automatically shut down and the solid rocket boosters wouldn't ignite, stopping the launch entirely. The walkway that the crew boarded on would swing back into place, and after checking over the situation, they would disembark and a full investigation would commence. This happened 5 times over the course of the shuttle's history, and on the first occasion, the astronauts narrowly escaped a deadly situation. When STS-41D aborted 4 seconds before launch, the crew evacuated around 40 minutes later only to be soaked by the pad deluge system and went down to the elevator. Unbeknownst to them, the deluge system was still running to try and suppress a hydrogen fire that had started around the engines, and that fire had, much earlier, crept all the way up to the outside of the shuttle to roughly where the service arm was, which the crew would have used immediately, but chose not to. Astronaut Charles D. Walker would later speak on this situation in an interview.
There was a fire on the launch pad, a hydrogen-fueled fire. It's invisible to the eye. So the cameras looking at the launch pad for launch control didn't even see it. Let me tell you, as they say in the aviation business, in the cockpit that morning, there was a pretty high pucker factor until we figured out that we were good and safe.
The next abort mode and all after it only took place after the solid boosters ignited and the shuttle had committed to a liftoff. However, because the SRBs couldn't be shut down, no abort could be begun until after they burnt out and separated at around T+2 minutes. So if an engine were to fail during these first 2 minutes, the crew would simply have to ride it out, even though the decision to abort would already be made, and this first flight abort mode was perhaps the most harrowing: return to launch site or RTLS. After booster separation, the vehicle would need to perform a powered pitch around, quite literally flipping itself over to face back toward the Kennedy Space Center. The OMS engines and reaction control thrusters would burn for the entire time to reduce the weight of its propellant, and the flip over wouldn't begin until sufficient main engine propellant had been burnt off as well. The shuttle would, after sending itself back towards KSC, pitch down, jettison the external fuel tank, and then glide back to the runway. An extremely difficult maneuver that astronaut Mike Mullane referred to as a, quote, unnatural act of physics. This abort mode was thankfully never attempted, nor was its even more dangerous sister maneuver known as 2-out blue. This would occur if, after the RTLS had begun, a second engine were to fail.
Left in, right engine out.
Need to push Capcom. We concur the left engine's out.
Left in, right engine down.
Need to push.
We concur the left in, right engine down.
2-out blue, buddy. Need to push button. Need to push button. 2 engine out blue.
You're in the 2 engine out blue. We need the push buttons.
At this point, the vehicle would be unable to reach the runway for a landing, and the crew would have to prepare for a glide into a crash landing in the water, which the orbiter could not survive, and then bail out of the vehicle at a very specific point during this glide to save their own lives. The next abort mode was TAL, or Transoceanic Abort Landing. This was to be used when RTLS was no longer possible, and if the failure was less time critical. In this case, it wouldn't flip around, but would change its trajectory to land at one of several air bases across the Atlantic Ocean. These landing sites changed over time due to both mission and geopolitical factors, but some included Istres Air Base in France and RAF Fairford in England. They would be selected well before the launch, with preparation taking a full week to deliver medical equipment and rescue workers to the sites. Again, much like RTLS, TOW was never used during the shuttle program. The next abort mode came if the shuttle was able to make it almost all the way to orbit, i.e. if it was able to circle the Earth once and land back at KSC. This would occur around 5 minutes into the flight, with the rest of the time just being raising its perigee, the lowest point in its orbit, to a sufficient altitude. However, if problems occurred and the decision was made to not fully enter orbit, the shuttle would proceed straight into re-entry and land either at KSC, Edwards Air Force Base, or White Sands. This option existed in a very small window and likely never would have been possible for an engine failure, but could have been used for a medical emergency. Once again, it never was used. The last abort option, and the only one actually used, was the abort to orbit or ATO. This occurred once a stable orbit was obtainable, but not the desired orbit. Typically, the shuttle would go somewhere between 320 to 480 kilometers or 200 to 300 miles up, depending on the objectives, but an orbit of 190 kilometers or 120 miles was considered stable. Once there, the shuttle would proceed to carry out its mission as best as it could. If the payload required a higher orbit to be deployed, it would be kept in the payload bay and flown again. We'll cover the one time it was used later, but for now, I'll just say the mission ended up being a success. Now, with all of that covered, let's finally get back to the timeline. Construction of the first test orbiter began in June of 1974, originally planned to be named Constitution. However, a letter-writing campaign to President Gerald Ford made a request. An official White House memo would later cite, quote, hundreds of thousands of letters that eventually convinced NASA officials to name the orbiter Enterprise after the fictional starship from Gene Roddenberry's Star Trek. When construction and initial ground testing was finished in 1976, Enterprise was rolled out of Rockwell's plant in California to a dedication ceremony that included Roddenberry himself as well as the principal cast of Star Trek, with the exception of William Shatner. There's no explanation for why Captain Kirk himself couldn't make it, though it wasn't unusual for him to be absent from events where most of the rest of the cast attended. At the beginning of the next year, Enterprise was taken to Edwards Air Force Base on top of the shuttle carrier aircraft, a modified Boeing 747, for operational testing. Initially acquired from American Airlines in 1974 for trailing wake vortex research, the SCA had most of its cabin insulation stripped and its fuselage strengthened to hold the weight of the shuttle. Mounting struts were added on top of it, one of which had this amusing technical note on it, just in case. The first 11 tests of Enterprise kept it attached to the SCA, measuring its flight characteristics and the capabilities of its computer systems, and the first 3 never even left the ground, being only taxi tests. Finally, on August 12, 1977, Shuttle Enterprise took flight for the very first time, piloted by C. Gordon Fullerton and Apollo 13 veteran Fred Hayes.
Take one step. 32 clear.
Hey, we got a GPC light, lost the sync on 2, pushing over.
And a big X on computer number 2.
Roger, standby and halt on GPC number 2. Go for mode 203.
Roger. Hey, she's flying good.
Roger.
Still with its protective tail cone attached at the rear, the shuttle separated from the SCA at an altitude of approximately 24,000 feet, and over the course of 5 minutes and 21 seconds made a carefully controlled glide down to a lakebed touchdown.
40 feet. 30. 20. 15. 10. Holding 10. 220 at about 5 feet. 4 feet. Getting some dust. 4 feet. 3 feet. 2 feet. Just over off about 2 feet. You're on. You're on. Okay, your nose wheel's about 10 feet. About 5. 4 feet. About 5 feet. 4, 3, 2, 1. We'll see you, babe.
Yes, it was great.
In the moment Enterprise separated from the aircraft, a master alarm sounded when one of the orbiter's 4 flight computers dropped offline, caused by a transistor dislodging. Fullerton quickly pulled circuit breakers and reset switches per procedure, and he noted that by the time he had done this, quote, "Hey, this is flying pretty good, because I was really distracted from the fundamental evaluation of the airplane at first." Hayes noted in later interviews that Enterprise handled better than the modified Gulfstream II that they used for simulations, stating that during touchdown, quote, "It was actually pretty smooth. I don't recall much noise. There wasn't a lot of time, and I don't recall vibration at all." After 3 flights, the tail cone was removed, and 2 more tests were performed, all without issues. Following these flights, Enterprise returned to the Marshall Space Flight Center to be mated with an external tank and dummy boosters for structural and vibration tests. Following this, it was flown to KSC to test the procedures of proper stack assembly within the vehicle assembly building, including doing mock rollouts to Launchpad 39A. By the time Enterprise had finished its approach and landing tests, the construction of the first spaceworthy orbiter OV-102 Shuttle-Columbia was well underway, having begun in 1975. Lessons learned during Enterprise's testing influenced Columbia's construction, resulting in several significant design changes to the fuselage and wings. While the initial plan had been to retrofit Enterprise into a full space shuttle, these design changes made it far too expensive to do so. Instead, Structural Test Article 099, built for very early vibration and structural tests, was chosen to be upgraded into the second orbiter Shuttle Challenger, resulting in its confusing designation of OV-099. Shuttle Columbia was finished and delivered to the Kennedy Space Center in March of 1979, intending to make its first flight late that year. It was brought to the orbiter processing facility with around 8,000 of its 30,000 thermal protection tiles not yet installed. At the same time, the SSME had just reached a final review. However, NASA had a requirement that the engines must undergo 110,253 seconds of testing before being used on a flight. After being installed on Columbia in 1979, they were removed again in 1980 for further testing, and then finally given a 20-second flight readiness test firing in February of 1981, at which point they were declared ready for flight. However, before Columbia could fly, tragedy would strike the program early. On March 19, 1981, Columbia was on the pad for a ground countdown test. The aft engine compartment was flooded with a pure nitrogen atmosphere to reduce the risk of an explosion or fire, and at the end of the test, pad workers were given clearance to go into the orbiter and continue work. However, the nitrogen had not yet been purged from the aft compartment when 3 technicians, John Bjornstad, Forrest Cole, and Nick Mullen, entered. They lost consciousness within moments from the lack of oxygen, and when another worker saw them and tried to help, he too passed out. A 4th alerted security and the men were taken out. Bjornstad would die at the scene, while Cole died a few weeks later in hospital. Mullen survived until 1995 with permanent brain damage due to complications from his injuries, and these 3 would mark the first incident of launchpad deaths since Apollo 1 in 1967. STS-1, the first flight of the program, was ready the next month. The crew, Gemini and Apollo veteran John Young and Robert Crippen, who would have flown in the cancelled Manned Orbiting Laboratory project, were selected back in 1978. Young was, at the time, chief of the astronaut office and stated that it seemed only right that he command this first mission. There was some question as to what kind of mission STS-1 should be. Management felt that a suborbital flight seemed like a proper, incremental step in testing the vehicle, landing Columbia at the emergency landing site in Senegal. A later suggestion came that STS-1 should be used to test the RTLS abort scenario, which was quickly overruled by Young himself. His veteran status gave his opinion weight, as he was the only person in the room who had set foot on the moon, and he recommended that STS-1 remain as a full all-up orbital test flight. On testing the RTLS abort, he stated, quote, "Let's not practice Russian roulette, because you may have a loaded gun there."
8, 7, 6, 5, 4, we run for main engine 7.
STS-1 would take flight exactly 20 years after Vostok 1, the world's first crewed spaceflight. Columbia lifted off from Pad 39A at 12 o'clock UTC on April 12, 1981. The Space Shuttle remains, to date, the only spacecraft to ever make its maiden voyage with human beings on board, mostly because it had to. Young and Crippen both noted that as the main engines ignited, the orbiter pitched down toward the astronauts' feet in a motion later referred to as the twang, before the boosters ignited and the vehicle lifted off. Shortly after clearing the launch tower, it rolled and pitched into a heads-down position for an optimal ride to a 40.30 degree orbital inclination. The main engines throttled back to 65% to move through max Q, the period where the vehicle undergoes the maximum amount of aerodynamic pressure as it accelerates faster than the atmosphere becomes thinner around it. The performance of the SRBs was slightly better than expected, making its trajectory a little more lofted than intended before they were jettisoned at 2 minutes and 12 seconds into the flight. At 8 minutes 32 seconds, the main engines cut off and the external tank was jettisoned. The OMS engines then burned for just under a minute and a half to insert Columbia into a roughly circular orbit of 246 by 248 kilometers, or 153 by 153 miles. Throughout this entire process, John Young's heart rate never went above 70 beats per minute, the normal resting heart rate. Robert Crippen, on the other hand, was up around 144 beats per minute. Young later said his heart, quote, was too old for it to go any faster. This isn't to say Young wasn't nervous. He would also later say that, quote, anyone who sits on top of the largest hydrogen-oxygen fueled system in the world, knowing they're going to light the bottom and doesn't get a little worried, does not fully understand the situation. STS-1 had very basic goals. Get to orbit safely, make sure everything was working well, and then come home. Once on orbit, Young and Crippen unstrapped themselves and opened the payload bay doors, noting some damage to the thermal tiles on the OMS pods. They then spent the next 53 hours doing systems tests, tracking the performance of the inertial measurement unit, testing the RCS systems, purging the fuel cells, doing photography, testing the hydraulics, and monitoring the radiation exposure. By April 14th, after completing 36 orbits, Columbia was ready to return home. After powering up the APUs and closing the payload bay, a 160-second deorbit burn was performed with the OMS engines over the Indian Ocean, putting her on a path back towards Edwards Air Force Base in California. Entering the atmosphere over the eastern Pacific Ocean at around 100 kilometers or 62 miles, a pink glow from the ionized air during re-entry could be seen out the windows. Most of the roll and banking maneuvers were performed automatically, both to allow the vehicle to further slow down by presenting a larger surface area to the atmosphere, and to adjust its trajectory to bring it closer to its intended landing zone. As Columbia went subsonic, Young took control, making a wide left turn to line up with Lakebed Runway 23, followed by a T-38 jet trainer escort. Columbia touched down its main gear at 339 kilometers an hour or 221 miles per hour, and as she rolled to a stop, Young remarked that, while on the surface, STS-1 seems like it was a complete success, there were several anomalies that would need to be resolved before the next flight, some of which were extraordinarily dangerous. The biggest issue, similar to anomalies during the first all-up test flight of the Saturn V, was a severe underestimation of the amount of vibrations caused by the engines, specifically the solid rocket boosters. The force of their ignition sent shockwaves down that bounced back up into the orbiter's tail section, bending fuel tank supports and stressing the lifting surfaces, the latter of which could have caused issues landing had the wing flaps sustained serious damage. As the vehicle ascended, the SRBs created an overpressure wave, damaging an RCS oxidizer strut and pushing the body flap beneath the main engines into a dangerous angle. While simulations expected that such an angle would crack or rupture the flap's hydraulic systems, making a controlled descent entirely impossible, this thankfully didn't happen. John Young would later admit that had he known about this, he would have aborted the flight via the ejection seats, and Columbia would have been lost on her very first flight. On orbit, examination of the rear of the vehicle showed significant damage to the tiles around the OMS pods, with around 16 of them being lost entirely. Unbeknownst to the crew until the post-flight briefing, a protruding tile gap filler had let hot gas into the gear well of the right main landing gear, buckling the landing gear door. Nevertheless, thankfully, none of STS-1's issues ended up being mission critical, and modification of the launch and re-entry procedures allowed for the program to continue after 103 days of Columbia being refurbished and more time spent modifying the program's procedures. Delayed from October of 1981 by a nitrogen tetroxide spill during the loading of the RCS tanks, Columbia's second flight was set for November 2, 1981. X-15 pilot Joe Engel and Richard Truly took the helm, both making their first true spaceflight on STS-2. Modifications to the sound suppression system allowed the launch to go exceptionally well, marking the first reflight of a spacecraft in history, though there was one anomaly that would darkly foreshadow the future of the program: O-ring blowby. The large rubber rings in the boosters, intended to seal gaps in the casing formed by the stress of ignition, experienced an anomaly in which hot gases blew past the seal of the rings, and after the damage was discovered, several flight simulations were performed to assess the danger. The anomaly was endorsed as a non-issue and would occur 14 more times until it finally caught up with the questionable safety of the program. Another issue can be heard over the radio during the launch process. A master alarm went off a little over 40 seconds into ascent. After reporting it back, the crew were told to ignore it, as it ended up being due to cabin stretch. Essentially, the orbiter's hull was expanding slightly as the stress of ascent took hold. This expansion also expanded the atmosphere inside, which sensors mistook for a sudden drop in pressure. These sensors would later be modified to account for cabin stretch in order to keep false alarms down.
Columbia, Houston, you're go at 40.
Roger, go at 40. And master alarm, and it's the
48 seconds, throttling down from execute.
Roger, ignore the master alarm, Columbia.
okay.
Nevertheless, Columbia reached orbit safely after discarding the second and final fuel tank to be painted white, an effort that would be ditched going forward to save on launch weight. This was planned to be a much longer mission than STS-1, spanning 5 days testing the shuttle imaging radar, a host of other experiments, and most importantly, the shuttle robotic arm, commonly known as the Canadarm. While the arm was successfully operated in all of its various modes at least once, the flight was cut short when, only 5 hours into the mission, one of 3 fuel cells began to act erratically. Engel and Truly were ordered to shut it down, and at this point, flight rules dictated that the mission could only last approximately 54 hours total. Despite this issue, the crew endeavored to achieve as much as possible with the time they had left. In addition to initial Canadarm tests, various onboard experiments performed themselves, and tests of the OMS engines were performed to ensure the shuttle could adjust its orbit during a mission. Columbia returned to runway 23 of Edwards Air Force Base on November 14th after 37 orbits, a perfectly textbook landing that revealed no lost tiles this time around. STS-3 would be the only mission to land at White Sands in New Mexico, which had some interesting results. Many of the goals were quite obvious: spend time doing everything that the previous mission could not, further test the robotic arm, as well as perform thermal exposure testing of the orbiter. They would change Columbia's orientation on orbit to see how different parts would react to prolonged exposure to direct sunlight, including the tail, nose, and the top. The bottom was designed to withstand exposure to heat, and thus was of lower concern. One notable result of this would be the discovery that leaving the payload bay doors exposed to sunlight for too long would cause them to warp slightly, which caused difficulties in fully closing them. The solution was obvious, much like the rotisserie maneuver used by the Apollo CSM, allowing the orbiter to slowly rotate on its roll axis would even out the temperature distribution. However, this would not always be possible, as some future experiments would require the orbiter to stay oriented away from the Earth in order to perform their functions. This flight also carried the first onboard experiments in the middeck, primarily exposure experiments that would test how different components would behave in microgravity. There were also instruments mounted in the payload bay, some to test how the orbiter itself was contaminating the area around it, and another to detect X-ray particles from solar flares. There was also a test candidate for a program called GAS, the Getaway Special. This was a program that offered individuals or groups opportunities to fly small experiments aboard the shuttle for relatively cheap. A 60-pound payload cost around $3,000 to carry into orbit, while a 100-pound payload would cost about $5,000. Perhaps the most interesting aspect of STS-3 occurred during descent and landing. The original intention had been to land at Edwards like the previous 2 flights, but flooding caused by excessive rain forced Mission Control to move it to White Sands Space Harbor in New Mexico. Ironically, on March 29, 1982, White Sands would experience its worst wind and sandstorm of the last 25 years. Left behind by this storm was a lot of disturbed gypsum dust. Very fine, like talcum powder, recalled astronaut Charles Bolden. The conditions were not ideal, but the storm was over by March 30th, so the decision was made to land. However, STS-3 had one more surprise in store. 10,000 feet above the ground, pilot Jack Luzma activated an experimental auto-land capability that it was hoped could be used later. The crew was deeply concerned that, if some glitch in this system took the vehicle off course during a critical moment, taking back control might be impossible to do in a timely manner. "We recommend that this was not a good thing to do," Bolden said. "You're asking a person who's been in space to take over in this dynamic mode of flight and land the vehicle safely. Their physical gains, their mental gains, their balance, everything's not there." The auto-land was demonstrated to an altitude of about 500 feet or 150 meters, at which point Luzma took over and deployed Columbia's landing gear. However, the wheels took longer than anticipated to fully deploy, locking into place only a few seconds before they touched down. Columbia came in faster and further down the runway than anticipated, and just as her nose was rotated down toward the flight deck, it promptly sprang back up. What they hadn't realized was that the auto-land system, no longer controlling the roll, was still controlling the pitch. When this was noticed, Luzma pulled back on the stick to retake control, causing the nose to lift again before finally touching down fully. The harsh touchdown left a cracked rotor in one of the brakes, but the bigger concern was the gypsum dust. It seeped into every nook and cranny, every possible place it could embed itself, and never left. Columbia underwent extensive cleaning during her refit, but several flights later, crew members reported still seeing some particles floating around once she reached orbit, and this would continue to be reported until Columbia was lost a full 21 years later. A little morbid to think about, but there's probably still some gypsum dust from New Mexico scattered around Texas to this very day. STS-4 would be the final of the initial test flights of the shuttle program. Launching 4 months after the previous flight on June 27, 1982, this would also fly the first proper payloads. 9 scientific experiments from Utah State University flying within the Getaway Special canisters, as well as a classified Air Force payload. Commander and Apollo veteran Ken Mattingly would later describe the classified payload as a, quote, rinky-dink collection of minor stuff that they wanted to fly. More specifically, they were sensors to detect missile launches, and they didn't work. The Canadarm was also used with a new instrument mounted on it designed to examine the gases or other particles that the orbiter put into space around it during its flight. A largely uneventful flight, Columbia touched down on a concrete runway for the first time 1 week later at Edwards AFB. Its solid rocket boosters from the launch weren't recovered as their parachutes failed, one of the only 2 flights where a recovery didn't occur. After disembarking, the crew were greeted by President Reagan and his wife Nancy, after which Reagan gave a speech that declared the Space Shuttle program officially operational. By now, Shuttle Challenger was long since assembled, and Discovery and Atlantis having begun, completed in October of 1981. It was delivered to KSC just 1 day after STS-4 landed, and in fact, while the crew delivered their own speeches following President Reagan, the shuttle carrier aircraft was flown overhead, carrying the brand new orbiter on its way to KSC. It still had some final flight readiness testing to go through, so the first operational shuttle flight would continue with Columbia. Ready to go again with the first 4-person crew and the first deployed payloads, STS-5 launched on November 11, 1982. 2 satellites, both Hughes-built HS-376 series, and therefore roughly identical in appearance, were held in clamshell-shaped sunshades in the payload bay, and once deployed, used attached upper stages to push themselves into geosynchronous orbit. The mission was supposed to include a spacewalk as well, however the suits on board were found to have faults including a broken recirculation fan and oxygen regulator, forcing the EVA to be cancelled. And at this point, I think we'll need to take a moment to talk about those suits. You may know that, up until this point, NASA only had 2 spacesuits capable of EVA work. First the Gemini spacesuit, which had mixed results and was often very difficult to maneuver in, and then the Apollo suit, which was improved somewhat but was very expensive, with several unused Apollo suits being repurposed and used in the Skylab program. New suits for the shuttle program, named the Extravehicular Mobility Unit or EMU, were first contracted to Hamilton Standard and ILC Dover in 1974. Consisting of 2 primary parts, a torso section and a lower leg section, there are actually several individual pieces that are assembled as they're donned. Astronauts wear a thermal control undergarment, a maximum absorbency garment, basically a fancy diaper, a liquid cooling garment on top of that, and then don the suit itself piece by piece. The suit includes a control panel on the chest that allows astronauts to use the radio, check the suit pressure, use purge and cooling control valves, and more. Beneath this control panel is a modified mini workstation system which can hold a number of tools during the spacewalk. On the back of the hard upper torso assembly is the primary life support system, and below it is a secondary oxygen pack for emergencies. The first EMU suits were shipped to NASA in 1982, and there's a lot more I could say about them, but we just don't have time. If you'd like to learn more, I'd recommend my video A Brief History of Spacesuits, which goes into more detail about all the suits NASA and others have used over the years. Shuttle Challenger made her debut flight in April of 1983 after 2 flight readiness tests were conducted to assess a possible hydrogen leak. It carried the first Tracking and Data Relay Satellite or TDRS, intended to aid in space communications during longer duration spaceflights by giving an extra communications point outside of ground tracking stations. TDRS-1 was contaminated on the pad when a storm hit, forcing it to be returned to its checkout facility and further delaying what was originally supposed to be a January launch date. Combined with the engine issues, Challenger finally took off on April 4th, marking the first use of a new lightweight external tank and SRB casing that allowed for increased payload capacity. The TDRS-1 payload was released from the payload bay approximately 10 hours after launch, and while the deployment was successful, it quickly experienced problems with its inertial upper stage. It tumbled out of control, and the firing of its solid rocket motor sent it into a low elliptical orbit. Thankfully, it held far more propellant for its reaction control system than was needed, and over the course of the next several months, its thrusters were fired in intervals to gradually move it into the intended geosynchronous orbit. On flight day 4, astronauts Story Musgrave and Donald Peterson donned the EMU suits and headed out into Challenger's payload bay. It was very much a proof of concept. Over the course of 4 hours, they tested spacewalk operations, moving along the shuttle's handholds, the suits themselves, and any procedures that might be needed should an emergency spacewalk need to be performed. The mission was a complete success. The cadence of the program began to ramp up. STS-7, Challenger's second flight, carried NASA's first female astronaut Sally Ride in June of 1983. It also marked the first use of the Shuttle Pallet Satellite, or SPAS, a satellite bus designed to be deployed by the Canadarm and then later retrieved. This allowed a camera mounted aboard the bus to snap the first photos of a space shuttle in orbit from a third-person perspective. On the less than ideal side, STS-7 was the first flight to experience foam shedding of the bipod ramp, a problem which would eventually result in the loss of Columbia almost 20 years later. However, as this was the first of such incidents, the incident was treated as an in-flight anomaly and no corrective actions were taken. STS-8 would carry the first African-American astronaut, Guion Bluford, but again would experience a launch anomaly. While Challenger reached orbit safely and without any issues, post-flight inspection of the SRBs discovered severe corrosion in the left side booster. If the booster had fired for only 14 seconds longer, it could have ruptured and caused a loss of control and probably loss of the entire flight. While it wasn't widely reported by the media, NASA did realize the severity of the issue this time, finding fault in the batch of resin used for this set of boosters and changing out the nozzles for the next flight. STS-9 saw the first flight of the Space Lab module. As NASA no longer had a semi-permanent space station in the form of Skylab, a temporary solution was implemented while planning for what would eventually become the ISS. Space Lab, a cylindrical pressurized module with an external pallet for payloads, allowed the shuttle to become a space station unto itself, albeit limited to use for about 2 weeks at a time. This first flight, a joint NASA and ESA operation, was dedicated to demonstrating that Spacelab was a feasible way to perform microgravity research and was considered entirely successful. One thing I would like to note about Spacelab, which I covered in my Space Shuttle Iceberg video, is one of the more insane aspects of the shuttle program, the Spacelab contingency procedure. Spacelab was attached to the shuttle via the airlock, making a spacewalk via the payload bay impossible. If an astronaut did need to go outside during a shuttle mission, it would have to be via the hatch on the middeck. One such situation this might be necessary for is if the payload bay doors failed to close correctly. In this situation, an astronaut would need to leave via the hatch, enter the payload bay, and manually close the doors from the inside, ensuring they latch correctly. However, the astronaut would then be unable to get back into the shuttle. They would have to then attach themselves to a handhold, turn their suit temperature down to the lowest possible setting, and hold on for dear life all the way through atmospheric re-entry and landing. Thankfully, such a scenario never needed to be explored in practice. At this point, Shuttle Columbia was taken out of service temporarily for renovations, and the program switched up its numbering system. Now, flights were to be designated STS-AB-C, where A represented the fiscal year running from October to September, 4 being 1984, 5 being late 1984 to 1985, etc., B representing the launch site, 1 for KSC, and 2 for Slick 6, though Slick 6 never ended up being used, and C being the planned chronological sequence of launches from that site in that fiscal year. Intending to support a high-rate flight manifest, delays and later incidents made the desired high cadence impossible, and one of the digits in the sequence was never even actually used, making it extremely confusing for both the public and the media. The first of these flights, STS-41B, saw another noteworthy event, the world's first untethered spacewalk. The Manned Maneuvering Unit, or MMU, a successor to the unused Air Force Astronaut Maneuvering Unit from Project Gemini, was developed to allow astronauts to leave the shuttle payload bay in order to capture or service orbiting satellites without a tether attached to them. The unit was first tested by Bruce McCandless on STS-41B, moving to a maximum of 322 feet away from the orbiter and then back again. My favorite part of this is the post-flight presentation, in which Bruce sounds like he's describing a casual trip to the nearest gas station for a bag of Doritos.
Here I am, I guess, backing out to 150 feet, coming back in, and then out to 300 and coming back in.
The MMU saw its first practical use on the next flight, STS-41C. First, the mission deployed the Long Duration Exposure Facility, a 12-sided experimental cylinder containing 57 different scientific experiments to be retrieved by a later flight. Next, Challenger maneuvered close to the Solar Maximum satellite, which had deployed in 1980 aboard a Delta rocket but suffered an attitude control failure. Astronaut George Nelson, using an MMU and a capture tool called TPAD, then approached the satellite. He made 3 attempts to clamp the T-pad to the satellite, but failed, and the satellite began to tumble when Nelson attempted to grab a solar array with his hand. The spacewalk was called off until ground control was able to stabilize the spin, and the satellite was grappled using the robotic arm instead. At this point, you may begin to see why the MMU didn't last very long. Most of what it could do could also be done with the Canadarm. The next mission would see the debut of my personal favorite orbiter in the fleet. Delivered to KSC in November of 1983 and having his flight readiness firing in June of 1984, OV-103 Shuttle Discovery, alongside Challenger, were given modifications to accommodate the Centaur G booster, a powerful cryogenic-fueled upper stage that was to be used to deliver heavy deep space payloads to the outer planets. She was earmarked for DoD flights and was intended to be used for the first launch from Vandenberg. While Columbia and Challenger are easily discernible due to Columbia's distinctive black shines, Discovery has its own feature that makes it unique when its name is invisible. Near the middle starboard window, several black tiles were installed where there should have been white tiles, and this never needed to be fixed, so Discovery permanently had what was affectionately referred to as her teardrop.
10. We have a go for main engine start. 7, 6, 5. We have main engine start. We have a cutoff. We have an abort by the onboard computers of the orbiter Discovery.
Discovery's maiden voyage, STS-41D, saw the first on-the-pad abort on her second launch attempt at the end of June, which we talked about previously. At T-4 seconds, an RSLS abort was triggered, and at that time, the center engine hadn't yet started. This caused confusion among the flight controllers, who were unable to verify the engine's state and thus didn't immediately recognize the invisible hydrogen fire burning on the pad. This led to changes in the abort procedures. Now the fire suppression system would activate immediately during any abort, and the slidewire escape system was to be tested with a real person prior to the next launch attempt. As this had never been done before, it was revealed later that launch controllers were reluctant to order an evacuation, worried the crew would be injured by the escape system. STS-41D launched successfully on her 4th attempt. The first was scrubbed due to a computer glitch, the second aborted, and the third scrubbed due to discrepancies with the SRB fire commands, on August 30th. In addition to deploying 3 communications satellites, Discovery also carried the OAST-1 solar array. This prototype extendable array, which stretched up out of the payload bay to a height of 102 feet, was used to demonstrate the feasibility of large, lightweight solar panels for use on future space stations, most notably the ISS, which still didn't have its temporary name of Space Station Freedom at that time. This mission was also notable for having some of the most crystal clear launch and landing footage in the entire program, as it was filmed with IMAX cameras for the 1985 documentary The Dream is Alive. This documentary included a lot of themes regarding space travel becoming normalized, with the shuttle's feats making space travel more accessible and more affordable for the future. Unfortunately, just a year after its release, something would happen that heavily undercut this message. Even on this maiden flight of Discovery, Morton Thiokol engineers found damage to the SRB O-rings caused by blowby, calling it the quote, first big red flag on their safety. STS-51A in November of 1984 was Discovery's second flight and was something of a landmark. After deploying 2 satellites, the crew were then tasked with retrieving 2 more, which had been deployed by STS-41B. A failure of their upper stages had left them in improper orbits, and the final use of the MMU was utilized to retrieve them. The first, Palapa, was difficult. After being captured with a device called the Stinger or Apogee Capture device, it was brought to the Canadarm, which tried and failed to grapple it. Instead, astronauts Joseph Allen and Dale Gardner moved it to its cradle in the payload bay themselves. Following this, West Star 6 was recovered in a similar but less difficult manner, and Gardner humorously held up a for sale sign to the camera with the satellites visible in the bay behind him. Ironically enough, West Star was in fact sold to a Hong Kong-based satellite company called AsiaSat. This would be the last time an untethered spacewalk was performed until tests of the SAFER system in 1994, which was kept only for emergency purposes in the case of a problem with tethers. The next flight would begin classified Department of Defense flights, during which a shuttle would go up, do something, and then come back. Officially, that's all we would know about most of these flights, though over the years many elements were declassified. Most flights would either deploy a spy satellite or test military prototypes in orbit, with this first flight deploying a USA-8 signals intelligence satellite. From here, shuttle cadence hits its golden period throughout 1985. More satellites deployed, more Space Lab experiments done, and the next significant flight we can arrive at is STS-51F, the only post-launch abort in the entire program. The 8th flight of the Shuttle Challenger, this also featured the second RSLS abort, shutting down after the number 2 engine experienced a coolant valve malfunction at T-3 seconds.
It's 10, 9, 8, 7, 6, 5, 4, 3, 2. We have an RSLS abort. We have an abort.
GLS safing in progress. BFS and pass are showing 101.
GLS safing is in progress at this time.
On her second attempt, she lifted off successfully, but problems occurred around 3.5 minutes into the ascent. 2 temperature sensors on the center engine failed, 12 seconds apart, causing the engine to shut down. As this was well past booster separation, the decision was made to abort to orbit.
Lead copy, stand by.
Flight Fido, abort ATO. Abort ATO.
We have a center engine down.
Abort ATO. Abort ATO.
That is, continue into a stable but lower than intended orbit. Approximately 4.5 minutes later, a sensor on the right engine failed, and booster systems engineer Jenny Howard recommended the crew move to inhibit any further automatic shutdowns. If another had shut down, this might have resulted in a TAL abort, a transatlantic landing, considered quite dangerous.
Sensor problems. We've failed another sensor. I'm tempted to go inhibit it. I know we're single engine capability.
Are we past TAL, Fido?
Yes, we are, Flight.
Limits to inhibit.
Challenger Houston, main engine limits to inhibit.
However, Challenger successfully made it into orbit to carry out her mission. It carried 2 notable payloads. First, the carbonated beverage dispenser evaluation, sponsored in part by both Pepsi and Coca-Cola, using specially designed cans that could be easily consumed in microgravity. Only also had a giant infrared telescope, I guess. The Spacelab Infrared Telescope used for mapping diffuse cosmic infrared emissions, as well as a test of the Space Shuttle as an astronomy platform, as it was thought that heat, glow, and outgassing particles from the shuttle might obscure the more sensitive observations. 2 flights later, the 4th shuttle would join the fleet, OV-104 Atlantis. There isn't much to say about the flight though, as it was another DoD flight, merely deploying 2 defense satellites. Her second flight was more unique, STS-61B in November of 1985. In addition to deploying 3 satellites, this flight also performed an experiment on assembling large structures in space, EASE and ACCESS. EASE stood for Experimental Assembly of Structures in EVA, and ACCESS stood for Assembly Concept for Construction of Erectable Space Structures. The primary purpose was to study how easily astronauts could pick up the concepts of the assembly process while in space, as well as how much such activities would physically drain them. The really tricky part of assembling things in space has to do with microgravity. If you're free-floating and you apply pressure to something, such as when fitting 2 pieces together or pushing a drill against a bolt, there is an equal and opposite physical reaction that will push you away from the task at hand. The astronauts experimented with different techniques for bracing themselves and handling moments of inertia. After having practiced the process in neutral buoyancy training, the astronauts actually found the process much easier in true microgravity, assembling the EASE structure 8 times, which was twice more than had been planned. The experiments were considered overall to be successful, providing NASA with a framework that they would need to plan out the later assembly of the International Space Station. Throughout 1985, NASA had been pushing the shuttle program hard. It was already unable to meet the expectations that its initial concept had set. External tank production and turnaround times were simply too slow. However, NASA was still doing everything they could to tout the shuttle as the future of spaceflight, with documentaries like The Dream is Alive focusing on making it seem routine and more accessible than it ever had been before. To amplify this, President Reagan announced the Teacher in Space project to inspire students and spur interest in STEM subjects. Multiple civilian teachers would go to space via the shuttle as payload specialists and then return to share the experience with their students. The first teacher astronaut to be selected was Krista McAuliffe, then a social studies teacher at Concord High School in New Hampshire. She was scheduled to fly on the 10th flight of Shuttle Challenger, STS-51L, and this is where the entire shuttle program began to fall apart. Originally scheduled for July of 1985, STS-51L was pushed back to November and then to January of 1986. On January 22nd, it was delayed another 6 days due to dust storms at one of the shuttle's emergency landing sites in Senegal. A thunderstorm forecast at the Cape for the 26th postponed it again by another day, and then during the first attempt on the 27th, the countdown was halted at T-9 minutes. The crew cabin's door handle couldn't be removed due to a stuck bolt, and thus an insulation tile that was supposed to be installed over top of it couldn't be. By the time the issue was resolved, high winds had forced a scrub of the entire launch, making one final delay until January 28th. All of these delays were ridiculed by the media, as the Teacher in Space program had put increased eyes on the launch. CBS's Dan Rather referred to the bolt issue as a, quote, high-tech low comedy, and spectators for the launch were growing frustrated with the increasing wait time. All of these delays were due to safety concerns, and in fact were made more critical by the increased public attention, but frankly, the general public doesn't understand that. All they see is that the shuttle still isn't launching. January 28th was scheduled to be a particularly cold day, rising to only -3 Celsius or 16 Fahrenheit at the scheduled time of launch. Morton Thiokol engineers began to raise concerns the previous evening, believing that the O-ring seals in the SRBs wouldn't extrude quickly enough to seal the gaps in the casing. As this was a record cold temperature for a shuttle launch, they didn't have enough data to say for sure that the launch process wouldn't be successful. Nevertheless, Morton Thiokol engineers Robert Lund and Joe Kilminster, vice presidents of engineering and the Space Booster program respectively, recommended against launching until the temperature was above 12 Celsius or 53 Fahrenheit, the previous record low for a shuttle launch. The conference call then held a recess to allow Morton Thiokol management to have a private discussion. Further examination of available evidence was done to stop Lawrence Malloy, the NASA SRB project manager, from accusing the engineers of delaying the launch with inconclusive data. When the conference call resumed, Morton Thiokol leadership had suddenly changed their minds. The evidence was inconclusive, and the margin of error for a failure or O-ring erosion was dubbed substantial. The decision was made to proceed with the launch. Alan J. McDonald, Morton Thiokol's director of the Shuttle SRM project at KSC, stated he would not sign off on the decision, but Malloy demanded Morton Thiokol provide a signed recommendation. Kilminster then confirmed that he would sign and fax the recommendation immediately, and Malloy made a call to the NASA mission management team without bringing up the O-ring concerns, with the two agreeing to proceed with the launch. Challenger lifted off at 11:38 a.m., and at first, everything seemed nominal. However, internally, everything was quickly moving toward catastrophe. The O-rings in the right side SRB had failed to seal the gaps in the casing. This could even be seen in post-launch photos, with the gray smoke escaping from the booster directly following the liftoff. However, melted aluminum oxides created by the burned solid propellant unintentionally sealed the joint, creating a temporary barrier. However, as the vehicle passed through the area of maximum dynamic pressure at around T+37 seconds, the wind shear and the intense forces shattered the seal, allowing flames to escape from the joint. This became visible on the tracking cameras and caused the pressure within the SRB to drop. This plume also created a leak in the external tank, and the main engines began to pivot to compensate for this sudden uneven thrust. At T+68 seconds, capsule communicator Richard Covey told the crew,
"Challenger, go with throttle up." Challenger, go with throttle up.
This was the last communication heard from Challenger. At T+72 seconds, the right SRB pulled away from its aft strut attaching it to the external tank, and pressure in the liquid hydrogen tank suddenly dropped. 1 second later, the dome on the bottom of the tank fell off from the damage caused by the SRB plume. The fuel in the tank was promptly ignited, and the right SRB slammed into the intertank structure. The failure of the fuel tanks created what's called a boiling liquid expanding vapor explosion, in which most of the liquid fuel immediately evaporated back into gas. The entire stack pitched into an attitude it couldn't handle at Mach 1.92, and everything disintegrated into several pieces. The SRBs survived the breakup, continuing to fly unguided until range safety destroyed them in the air. The crew cabin separated in one piece from the rest of the orbiter, traveling in a ballistic trajectory. It's believed that at least some of the crew were still alive and conscious at this point, as 3 of the personal egress air packs had been activated. However, when the cabin hit the ocean surface at 207 miles per hour or 333 kilometers an hour, the 200 Gs of acceleration sealed their fates. Commander Richard Scobie, pilot Michael Smith, mission specialists Ronald McNair, Ellison Onizuka, and Judith Resnick, and payload specialists Gregory Jarvis and Krista McAuliffe were dead. That evening, President Reagan addressed the nation in a speech considered one of the most significant speeches in U.S. presidential history. On the 31st, he and Nancy Reagan spoke at a memorial service at Johnson, and T-38 Talon jets flew over the scene in the traditional missing man formation. On the same day, the U.S. Navy was tasked with recovery operations, prioritizing the SRBs to investigate precisely what had happened. When they found the crew compartment, Gregory Jarvis's body floated away and was lost to the recovery team. Astronaut Robert Crippen, frustrated by the team's failure to relocate Jarvis, reportedly rented a fishing boat at his own expense in an attempt to find him. Eventually, Jarvis's body was relocated several weeks later by the dive team. The official commission to investigate the accident, the Presidential Commission on the Space Shuttle Challenger accident, also known as the Rogers Commission, was formed on February 6th, with notable members such as astronauts Neil Armstrong and Sally Ride, physicist Richard Feynman, and record-setting test pilot Chuck Yeager. They held hearings to discuss the accident and the circumstances surrounding it. After only 9 days, Chairman William Rogers issued a statement that the Commission would be investigating the accident independent of NASA, as the agency had failed completely in its own internal processes. After over 160 interviews, 35 investigative sessions, and the involvement of over 6,000 people, the Commission published a report on June 6, 1986. In addition to determining the root cause of the accident, the report was deeply critical of both NASA and Morton Thiokol, concluding that NASA lacked a sufficient safety culture to properly report and analyze these issues. Pressure to increase flight rates was affecting training, quality control, and repair work. Redesigns of the SRB joints to prevent O-ring blow-by were proposed, as well as a complete restructuring of shuttle program management. An office for safety was to be established, and a means for the crew to escape during gliding flights was to be added. Richard Feynman in particular was viciously critical of NASA, demonstrating the O-ring failure using a simple piece of rubber and a glass of cold water in a televised hearing, and butted heads with Rogers on being more harsh towards NASA. He threatened to remove his name from the report entirely, arguing that multiple components of the shuttle, including the main engines, were far more dangerous than NASA had originally estimated. Now, I'm no physicist, but while the harsh criticism was merited, I'm not sure about the main engines. They only failed once out of 405 flights, 3 for each mission, and that failure was due to a temperature sensor, not the engine itself. In fact, the RS-25, as it is now named, is generally regarded as one of the more reliable rocket engines in existence. The shuttle program remained grounded for 32 months while changes and fixes were implemented. A new orbiter, Shuttle Endeavour, was approved for construction in 1987. The SRBs were redesigned, and crews would now wear pressurized suits during ascent and re-entry, something I went into during my History of Spacesuits video. The Teacher in Space program was cancelled, as was the MMU, launches from Slick 6, the Shuttle Centaur upper stage, and broad plans for frequent civilian passengers and commercial deployments. Vandenberg launches had even been planned to a point where crews, orbiters, and whole missions had already been selected. STS-62A went so far as to have Shuttle Discovery delivered to Slick 6 for fit checks, and was to be tasked with delivering a reconnaissance satellite into polar orbit. Many satellites were directed to uncrewed rockets, DoD-dedicated missions were cancelled or remanifested, and the Manned Spaceflight Engineer program intended to train military personnel as payload specialists was also cancelled. The launch cadence would be reduced, and the shift to expendable rockets for commercial satellites would take pressure off the agency by removing the reliance on a single launch vehicle. The entire shuttle program had been effectively gutted and would never, ever be the same. Before we move on, let's end this tragedy on a lighter note with some obscure trivia I covered in my Space Shuttle Iceberg. A piece of Challenger, in a way, survived the disaster and actually continued to fly for the rest of the program. This is because it was on Atlantis. At some point in 1984, Challenger had a problem with its body flap, with repairs taking longer than they wanted and potentially delaying her next flight. To speed up the processing time, the body flap was swished with that of Atlantis, which is the one Challenger took to her doom. This body flap that washed up on Cocoa Beach wasn't originally part of Challenger. The original was repaired and eventually mounted on Atlantis. What this means is that a piece of Shuttle Challenger was kept active for the entire remainder of the shuttle program, and today sits in the Kennedy Space Center Visitor Complex, still mounted on OV-104 Atlantis. 975 days after the loss of Challenger, in September of 1988, Shuttle Discovery lifted off from Launch Complex 39B after a few minor delays. Aboard her, among 4 other veteran crew members, was this man. Do you recognize him? This is Richard Covey, Capcom for Challenger's disastrous flight, and the last person to speak to Challenger's crew. The primary goal of this flight, STS-26, was to deploy a TDRS satellite, but secondary objectives were considered just as important. This was the debut of the launch entry suit, which would now be worn both during ascent and during atmospheric re-entry. A partial pressure suit nicknamed the Pumpkin Suit, it was designed to keep the crew alive and conscious in the event of a sudden depressurization. It was also flame resistant, and its bright color allowed for easy identification by search and rescue teams. It also included a survival backpack that held a parachute and other necessities, and again is something I covered much more extensively in a brief history of spacesuits. Those suits would be especially useful during a new phase of the mission introduced on this flight, a very brief window during which the crew was capable of bailing out. Unfortunately, this window occurred during the powered glide phase, and thus wouldn't have been helpful to the crew of Challenger, and consisted of a pyrotechnic mechanism on the side hatch, a long telescoping pole, and an assembly kit with hooks and lanyards. The pole would be mounted on the mid-deck ceiling, and the hooks and lanyards would allow the crew to, at just the right moment, slide down the pole to bail out of the orbiter, safely clearing the wing and OMS pods that they might strike on the way out otherwise. On the final day of the mission, the crew held a televised press conference, and each of them in turn said a few words in remembrance and reflection of the lost crew of Shuttle Challenger. Discovery then landed at Edwards AFB following a successful 4-day mission, though it was noted that a 12-inch piece of foam insulation had broken off the external tank and caused severe damage to the thermal tiles in the underwing area. You may already know what this is grimly foreshadowing, but first, we need to talk about a much worse mishap that occurred on the very next flight. STS-27, the third flight of Atlantis, was another classified DoD flight, though it's known today that it deployed a Lacrosse reconnaissance satellite. The launch looked nominal on the surface, but when reviewing the footage while the crew was in orbit, it was discovered that about 85 seconds in, a piece of insulating material from the nose cap on the right side solid rocket booster broke off and struck the starboard side of the orbiter's underside. The crew used the Canadarm to get a look at the damage, but the cameras weren't the best quality, making it difficult to see just how bad it was. What was worse, due to the mission being classified, they had to send images back to Mission Control via a slow encrypted transmission method, which further reduced their quality. Mission Control dismissed the damage, saying it looked to be mostly, quote, just lights and shadows, a response that the crew did not like. Commander Robert Gibson stated, after seeing the damage for himself, quote, "We are going to die," and all of the crew members expressed concerns about the safety of the vehicle during re-entry. Prior to getting ready to head home, Gibson told the crew to relax, stating that there was, quote, "no use dying all tensed up." However, he later added that if he saw any signs that Atlantis was in trouble on her way down, he was going to get on the radio and, quote, "tell Mission Control what I thought of their analysis" before he perished. Atlantis would end up returning home safely, but the extensive damage was visible before she even put her main gear on the ground. Over 700 tiles had been damaged, and one was missing completely. By sheer luck, beneath this tile there happened to be an aluminum mounting plate for an L-band antenna which had partially melted and absorbed the heat of re-entry, preventing a burn-through to the rest of the orbiter. Now, I know you might be thinking, an aluminum plate? Really? Apparently, yeah. This came up during my Shuttle Iceberg video, with several comments mentioning that the mounting plate must have actually been steel or something a little more sturdy than aluminum. However, the official STS-27 National Space Transportation System mission report states, quote, "structural damage was confined to the cavity over a small antenna access door. The tin plating on the aluminum door was melted with aluminum appearing to be halfway between hardened and annealed. The door also had a small buckle. So, a tin covering which has an even lower melting point than aluminum, over an aluminum door which was partially annealed, meaning its chemical composition had been altered by the heat to become more malleable." The next big milestone for the shuttle program was the deployment of several deep space probes. At least 2 of these were initially planned to be launched with the Shuttle Centaur upper stage, which would have allowed for a more powerful burn out of the Earth-Moon system and thus a quicker arrival at their destinations and thus a longer life of their instrumentation. However, with Shuttle Centaur being cancelled, these probes would instead rely on the less powerful Inertial Upper Stage or IUS already utilized for the TDRS satellites and several others. Shuttle Atlantis deployed the Venus-bound Magellan probe on STS-30, which would arrive at Earth's hellish sister in 1990, performing observations that are still being studied today. 2 flights later, Atlantis would deploy Galileo, headed for Jupiter. Despite several difficulties, Galileo would become the first probe to orbit an outer planet in late 1995. While not a deep space probe itself, the shuttle's next major payload would peer into deep space and help us to unveil the secrets of the early universe. Well, eventually it did. STS-31, launched in April of 1990, would deploy the Hubble Space Telescope into low orbit and film the entire mission with IMAX cameras. Hubble was a long time coming, pretty much 20 years, though when first proposed in 1970 the project was called the Large Space Telescope. It had a complicated quest to obtain funding and was delayed again and again, not the least of which was caused by the Challenger disaster. Its complexity was wildly underestimated, taking over a decade to fully assemble, and continuous budget cuts contrasted harshly with its rising costs. Finally launching in 1990, Hubble was by then over budget by roughly 6 times its 1977 estimate, and what was worse, it was broken. Within weeks of launch, Hubble returned images that indicated the optical system was not quite right. It was unable to focus on distant objects, spreading the light over a wide area instead of concentrating it on a few pixels. The primary mirror had been ground to the wrong shape, causing a spherical aberration, and the flaw was only a 2.2 micron difference, roughly 1/50th the thickness of a human hair. This fumble, so tiny the eye couldn't even comprehend it, had turned NASA's big billion-dollar telescope into a massive boondoggle. You might remember a scene in The Naked Gun 2.5 in which a restaurant featured major disasters in history along the wall. Right there, between the failed Ford cars of the future and the 1906 San Francisco earthquake, is Hubble. However, given its high cost, Hubble had been built with servicing missions in mind, so its story and relationship with the space shuttle wasn't quite over yet. Shuttle Atlantis released the shuttle's final deep space payload later that year, the Ulysses Solar Probe, a joint NASA-ESA venture, again using the inertial upper stage. All further shuttle payloads would be confined to Earth's orbit, with expendable rockets taking on the responsibility of other big, expensive payloads, signaling the serious decrease in trust in the overall program at this point. Another noteworthy payload was the Compton Gamma Ray Observatory deployed on STS-37, the second of the Great Observatories program, which would launch 4 large, powerful space telescopes to examine different parts of the EM spectrum. While Hubble primarily observed visible light, the Compton Gamma Ray Observatory observed, well, gamma rays. In May of 1992, Shuttle Endeavour made her debut flight, retrieving Intelsat 603 and fitting it with a new upper stage as its original one had failed. This required the only 3-person spacewalk in history, one of which held a long-standing duration record of 8 hours and 29 minutes. Upon landing, Endeavour featured the first use of a new piece of equipment, the drag chute, deployed from beneath the tail fin, allowing for further deceleration and thereby less damage to the wheels. A few flights with significant crosswinds had led to some pretty severe brake seizing and related damages, and the chute was implemented to help mitigate this. STS-46 launched a rather unique payload, the Tethered Satellite System, or TSS. A joint venture between NASA and the Italian Space Agency, TSS would deploy a satellite after it was let out of the payload and allowed to drift away while attached to a tether. The intention was for the TSS system to get above 20 kilometers away from the orbiter and demonstrate control of a satellite during deployment and aerodynamic stability at flight altitude. However, the tether system jammed at only 840 feet, and TSS was eventually reeled in after several unsuccessful attempts to free the tether. 3 years after Hubble was launched, Shuttle Endeavour returned to it on STS-61 to finally solve the flawed mirror problem, among other things. Docking with the telescope for almost 11 days, the crew made a then unprecedented 5 spacewalks. The first replaced gyroscopes and electrical fuse plugs while preparing equipment for the next one. On the second, the 2 solar arrays, one of which was found to be severely bent, were removed and 2 new arrays were installed. The third removed the original wide field camera and replaced it with one that had built-in corrective optics for the spherical aberration problem, which itself was fixed on the 4th spacewalk, installing the corrective optics space telescope axial replacement. These so-called glasses for Hubble placed corrective mirrors in the light path which encountered the aberration on the 3 main cameras. The final EVA installed a new control unit for the solar arrays, then assisted in manually deploying them before final functionality tests were performed. All objectives were completed successfully, and NASA's boondoggle telescope was now fully functional. Around this time, 2 things happened. First, the less interesting part. The USA was established. No, not that USA, the United Space Alliance. Formed as a joint venture between Rockwell International and Lockheed Martin, the USA centralized the process of shuttle contracting, consolidating all of the heritage contracts into one. The USA would take responsibility for day-to-day shuttle operations as of September 1996, with the signing of the Spaceflight Operations Contract. They would handle mission design and planning, software development, astronaut and flight controller training, launch and recovery, flight operations, vehicle processing, and all other support activities. When Rockwell sold off its aerospace assets, ownership of their portion of the USA would transfer to Boeing. Once the shuttle was retired, the USA would attempt to find new business opportunities via the Constellation program, but as of 2014, they held no active contracts, and as of 2019, the company was fully dissolved. The second and more important thing was that the shuttle entered the era of the Shuttle-Mir program. In 1992, President George H.W. Bush and Russian President Boris Yeltsin signed the, quote, agreement between the United States of America and the Russian Federation concerning cooperation in the exploration and use of outer space for peaceful purposes. Nice and concise one there, thank you Government Ease. This marked the first collaboration between the United States and Russia since the Apollo-Soyuz test project in 1975. An earlier shuttle Salyut proposal had been made in the late 1970s, docking a shuttle to the single-module Soviet Salyut stations, but was never realized, and since 1974, the USA had no experience in long-duration spaceflight after ceasing the Skylab project. Shuttle-Mir presented a unique situation for NASA. The aging modular Russian station, first launched in 1986, was struggling greatly following the collapse of the Soviet Union, and NASA saw a multifaceted opportunity here. Allowing the shuttle to service and rotate crews aboard Mir would not only boost international cooperation, but would allow NASA for some in-the-field practice for space station docking and help prepare for what, by now, had become the International Space Station. The program went in stages. First, Russian cosmonauts would fly on the space shuttle. This began with Sergei Krikalev, the fabled last Soviet who was aboard Mir during the Union's dissolution, flying on STS-60 in 1994. At the same time, NASA astronauts flew on Soyuz spacecraft, beginning with Norman Thagard on TM-21. In February of 1995, Shuttle Discovery performed the first rendezvous to practice docking approaches. It came within 11 meters or 36 feet from the station, at which point Commander Jim Weatherby said, quote, "As we are bringing our spaceships closer together, we are bringing our nations closer together. The next time we approach, we will shake your hand, and together we will lead our world into the next millennium." Mir Commander Alexander Viktorenko then replied, "We are one. We are human." A few flights later, Atlantis made the first docking with Mir on STS-71 using the nadir end, or the Earth-facing end, of the Kristall module, which was fitted with an androgynous docking system not dissimilar from the system used on Apollo-Soyuz. 8 more missions would rotate the crews, deliver science, and do microgravity research all the way up until 1998, though the program was not without its difficulties. Mir was already getting old by the mid-1990s, suffering from power issues and repeated system failures. In 1997, it suffered a fire, forcing the astronauts to wear oxygen masks for a while the air was recirculated and cleaned up. Later the same year, a Progress docking practice attempt resulted in a collision which left the entire Spectre module depressurized and permanently sealed off. It started to look like Mir was falling apart, and it was a dangerous place for the shuttle to be visiting. This honestly could be pretty true. For more information, check out my video, A Brief History of Mir. However, despite difficulties, Shuttle-Mir provided the basis for a lot of what would soon become the ISS. After the program ended, the first module of the ISS, Zarya, was launched in the same year. Amidst the Shuttle-Mir program, regular flights continued. STS-82 performed a second servicing mission to Hubble, removing old spectrographs and installing new ones, as well as replacing data storage and gyroscope equipment. The next flight, flown by Columbia, was the only full failure to perform a mission despite a successful launch and landing. STS-83 returned from a planned 15-day mission after only 4 days, once a fuel cell anomaly forced a shutdown. Mission rules required all 3 fuel cells to be fully operational, and the mission was aborted, being reflown later as STS-94 3 months later. STS-95, launched in October of 1998, is notable for a couple of reasons. First, it's the only shuttle launch that was observed by a sitting US president, and in fact, is one of only 3 NASA launches ever to be observed by a sitting US president. In 1969, Richard Nixon watched Apollo 12 lift off amidst a rainstorm. In 2020, Donald Trump watched the SpaceX Crew Dragon Demo 2 launch. President Bill Clinton watched Discovery lift off in 1998 for a very specific reason. A rather important US senator was aboard. John H. Glenn, aged 77 at the time, hadn't flown in space since he became the first American in orbit in 1962. His return aboard Discovery made him the oldest person to ever reach Earth orbit, a record he holds to this day, though I suppose it is worth noting that the oldest person to ever go to space is Ed Dwight, who flew a suborbital New Shepard flight at age 90. As a result of his advanced age, much of John Glenn's second flight was focused on studying him. Glenn lobbied for 2 years to send him as a kind of science experiment to study the effects of spaceflight on a geriatric individual. Furthermore, he was an ideal candidate as there was existing data to compare against, being his Mercury Atlas flight when he was over 25 years younger. At this point, the shuttle program began what can be considered its final mission, assembly of the International Space Station. I'm going to skim over the details of some of this because, again, I've covered it in more detail in my video, A Brief History of the International Space Station. However, we'll still go over the major events as they happened, beginning with STS-88. After the Zarya core module was launched in November, Shuttle Endeavour brought the Unity module 2 months later. Unity was essentially a connection node, containing multiple docking ports that would allow various other modules to connect to it. Most Russian modules would be docked to the opposite end of Zarya, making Unity effectively a bridge between the Russian and US sections of the station. Installation of the module was achieved by first positioning the Unity module facing up out of the payload bay, then grappling Zarya with the Canadarm and connecting the two together. A series of spacewalks were then performed to connect power cables, deploy antennas, and cover up trunnion pins left over from mounting the module to the shuttle's payload bay. During this process, a thermal blanket floated away from mission specialist Jerry Ross, and as it floated and twisted away in microgravity, the crew snapped a few photographs. One of these photographs would go down in history as an alleged unidentified UFO, famously known as the Black Knight satellite. Around this time, the shuttles would periodically be taken out of service to receive upgrades. The primary change was the inclusion of a glass cockpit, officially known as the Multifunction Electronic Display System. This would switch out the CRT displays, electromechanical gauges, and other analog instruments with 11 full-color flat-panel LCD screens. Atlantis was upgraded first in 1998 to 1999, with the final upgrades completed in 2001 to 2002, modernizing the 1970s cockpits for the current day. Other changes were made at the same time. Weight reductions were made by replacing aluminum hardware with lighter composites, structural improvements were made to support ISS missions, and minor landing gear tweaks to reduce damage on mission return. Columbia flew her final pre-upgrade mission in July of 1999, STS-93. This mission would launch the shuttle program's heaviest payload ever, the Chandra X-ray Observatory. In fact, Columbia was the only orbiter physically capable of launching it. The other orbiters were outfitted for the ISS, giving them a forward external airlock and docking adapter that took up around 10 to 15 feet of payload bay space. Chandra and the attached inertial upper stage just barely fit Columbia's full 60-foot payload bay clearance. The deployment of the telescope went entirely nominal, though the same cannot be said for the launch itself. As Columbia's main engines ignited, a gold-plated deactivation pin, used to plug a liquid oxygen post in the injector, came loose, ejected by the high-pressure flow at supersonic speeds. It struck the hot inner wall of the nozzle, rupturing 3 of the coolant tubes through which super-cold liquid hydrogen flowed. In post-flight photos, the slow but steady hydrogen leak could be seen as a bright streak on the inside of the engine nozzle. However, the launch computer didn't find any violation of launch criteria, as the leak was exceptionally slow, and liftoff proceeded nominally for about 5 seconds. At this point, a half-second electrical short occurred in AC bus 1, causing a voltage drop that knocked out the primary controller of the center engine. Redundant controllers took over, but this left the system with 0 fault tolerance. Had something else happened, all engines could have shut down prematurely and led to an RTLS abort scenario. As it stood, these 2 problems caused an early cutoff of the main engines by about 0.15 seconds, leading to a slight underspeed and lower than planned orbit that was compensated for by the OMS engines. The flight was a complete success, though it did lead to redesign of the engine injectors and changes to the post-flight wiring inspections. STS-92 would bring the first section of the integrated truss structure to the ISS, which would also be used to temporarily hold the station's massive solar arrays, the first of which would be coming on the next flight. The flight after that would bring the Destiny Lab, the primary operating facility for the US portion of the station. Next would come the longer and improved Canadarm2, then the Quest joint airlock used to facilitate spacewalks by both the United States and Russia. Columbia would fly her final successful flight in 2002, STS-109. This took her to the Hubble Space Telescope, installing a new set of more advanced solar arrays, a new camera, a new reaction wheel assembly, and a new experimental cooling system. The next several flights would expand the ISS truss assembly and bring the mobile base system, which allowed the Canadarm2 to move along the truss structure on rails to wherever it needed to go. Following this, Columbia lifted off with the Spacehab research module on STS-107 in January of 2003. She would never return to the ground in one piece. After what appeared to be a successful ascent, post-flight imagery revealed one incident. At 81 seconds in, a piece of foam roughly the size of a suitcase broke off from the left bipod ramp of the external fuel tank. It struck the reinforced carbon-carbon panels of Columbia's left wing at a speed of around 426 to 573 miles per hour, or 686 to 922 kilometers an hour. On the second day of the mission, the strike was noticed by flight risk management teams, and program manager Wayne Hale requested on-orbit pictures of the wing to assess the damage. A team was brought together by engineers at NASA and the United Space Alliance. They began running simulations and mathematical models to determine the potential damage, with one Boeing model predicting that the thin aluminum structure of the wing would be exposed to atmospheric reentry gases. This model was largely dismissed, as it was originally calibrated for ice debris, and the foam was lower density, which should leave the damage short of any structural breaches. No actual test data existed when it came specifically to foam on RCC, forcing engineers to extrapolate their analysis. Multiple requests were made to the Department of Defense to use satellites to provide imagery of the orbiter. 3 formal requests reached upper management, but Mission Management Team Chair Linda Ham canceled them as of Flight Day 7. The crew was never asked to inspect the damage using the shuttle's robotic arm. By Flight Day 9, the team concluded that there was, quote, no safety of flight issue, designating the damage as a turnaround issue, meaning the shuttle would be fine for re-entry and landing, but significant time and effort would need to be dedicated to repair and maintenance after the fact. The crew was notified via email that there was absolutely no concern for re-entry. Shuttle Columbia began re-entry into the atmosphere on the morning of February 1, 2003. While everything seemed nominal to the crew, the damage to the left wing was allowing hot air to enter and melt the aluminum structure. Sensors that were equivalent to black box data began recording higher than normal temperatures and strains on the wing, but this data wasn't sent to the crew or ground control. The orbiter exhibited a slight yaw, leaning slightly to the left as the drag on the damaged wing increased, but the flight control system compensated so well that nobody noticed. By the time she was over the California coast, Columbia had begun to shed debris. Once she was over Utah, Arizona, New Mexico, and Texas, people on the ground could see large chunks breaking away from it as it streaked through the sky. A few minutes later, the crew would report to Mission Control that they had noticed a fault message indicating the left landing gear tires were losing pressure. While responding to Mission Control's acknowledgement of the tire pressure indicator, Mission Control lost contact as Commander Husband said,
Flight Max those are also off.
At this time, it wasn't clear that anything had happened. Loss of communication during re-entry was very common, with several dead zones occurring throughout the process. However, while Mission Control was in the dark, a master alarm was going off on Columbia's flight deck, and the vehicle lost hydraulic pressure and abruptly pitched up before entering a flat spin. There's evidence that the crew had, despite dizziness and disorientation, configured some switches to try and restore hydraulic pressure. At precisely 9 a.m., the orbiter broke up entirely, scattering her pieces down toward the ground. Mission Control continued to try and re-establish contact, unaware of the situation until they received a phone call that news stations were reporting the shuttle's destruction. Flight Director Leroy Kane then began contingency procedures.
Columbia, Houston, comm check. Columbia, Houston, UHF, comm check.
Flight, I'd like to stay where we're at.
Columbia, Houston, UHF, comm check.
Fido, when are you expecting tracking? 1 minute ago, Flight. GC Flight. GC Flight. Fly GC. Lock the doors. Copy.
Columbia was lost, as was her crew. Commander Rick Husband, pilot William McCool, mission specialists Michael Anderson, Kalpana Chawla, and David Brown, and payload specialist Elon Ramon. Around 5 hours later, President George W. Bush addressed the nation.
The Columbia's lost. There are no survivors.
Recovery teams searched for pieces of Columbia and her crew until May, recovering only 38% of the orbiter's total weight. NASA convened the Columbian Accident Investigation Board to analyze the disaster and determine precisely what went wrong at every step. Unfortunately, much of the process was déjà vu. NASA had relaxed after the lengthy period between now and the loss of Challenger and had once again created a lax safety culture. Foam strikes were a known issue at this point, and the agency had done virtually nothing to mitigate them. Communication and integration channels for problem discussion were severely lacking, and pressure to adhere to the ISS construction schedule was compounding the problem. The board also discussed several options for a possible rescue of the crew. Not that it would have mattered, since NASA didn't believe a loss of crew was an option that they were facing. Columbia would have been capable of extending its mission for up to 30 days, powering down some systems to further save power. The board considered the possibility of expediting the next launch, Atlantis on STS-114, to perform a rendezvous and transfer Columbia's crew. Columbia could have then been deorbited empty and remotely, disposing of it in the Pacific Ocean. Another option also considered on-orbit repairs, most notably removing the thermal tiles from low-risk areas, shaping them, and then stuffing them into the hole in the left wing. However, they did note that the likelihood of this succeeding was low at best. For the second time, the shuttle program was grounded. Continued construction of the ISS was delayed, and a serious redesign of the external fuel tank was performed. Foam was removed from the bipod ramps, replaced with electric heaters, ground imaging systems were improved, launch cameras were added to the tanks and boosters to observe the orbiters' bellies, and a boom sensor system was added to the Canadarm to inspect for damage on reaching orbit. Temperature sensors and accelerometers were added to the orbiters to detect any impacts during launch, and improved inspection procedures were introduced to ensure good condition of the orbiters during refurbishment. NASA introduced contingency plans for all missions going forward, the STS-300 series missions. Now, each mission would be accompanied by the preparation of a second shuttle that would be made ready to launch quickly, designated Launch on Need missions. These would include extra seats in the middeck, provisions to accommodate extra suits, and a system that would allow an uncrewed shuttle to be deorbited and landed remotely by mission control. A final conclusion of the Columbia Accident Investigation Board was a reclassification of the shuttle as a whole. Despite being officially declared operational after STS-4, the board stated that, quote, "It was in reality an experimental vehicle. Many anomalies were expected on each mission. NASA had an underlying culture of schedule pressure and normalization of deviance, essentially accepting problems that hadn't yet caused catastrophe as normal. Consider the O-ring blow-by anomaly that preceded Challenger, and the history of foam strikes that preceded Columbia. The board stated that thousands of flights were needed to certify airlines, while the shuttle had, by comparison, only a handful of flights, which seems like something of an unfair comparison, but again, I'm no expert. From the loss of Columbia onward, the shuttle would officially maintain its status as an experimental vehicle with an operational mission, as stated by Deputy Associate Administrator Wayne Hale in 2004. The program would continue only to complete the International Space Station, and its retirement in 2011 would be accelerated by the board's findings. 907 days after the loss of Columbia, Space Shuttle Discovery lifted off for STS-114 on July 26, 2005, bound for the ISS. While the launch once again seemed nominal, footage showed that debris had broken off the external tank yet again, prompting another postponement of future flights to perform further modifications. Discovery did, thankfully, perform her mission successfully, bringing a multi-purpose logistics module for resupply, as well as an external stowage platform to the station. Upon rendezvous, another new safety feature was performed. The shuttle did a full 360-degree rotation on its pitch axis, exposing the underside to the crew of the station to allow for inspection of any possible damage. The crew also used the new orbiter boom sensor system on the Canadarm to perform a close inspection of the leading edges of the wings, the nose cap, the crew compartment, and any other spot deemed a problem area. They did in fact find a problem. 2 areas of the orbiter's underside were found to have protruding gap fillers, used to prevent the tiles from chattering together due to the stress of launch. They were supposed to fall out before reaching orbit, but didn't, and even though they were expected to cause no problem for re-entry, it was still deemed acceptable to perform a spacewalk and pull them out by hand. The next flight didn't occur for another full year, launching Discovery again in July of 2006 on STS-121. If you're wondering why shuttle flight numbers simply didn't go in numerical order, the simple answer is that the missions are designated beforehand, and preparation time for each often changes throughout the process, leading to missions being launched out of the numerical order. This second safety test flight went more smoothly, with the foam shedding problem now seemingly more or less resolved. Assembly of the ISS continued with Atlantis on STS-115, adding another truss segment and another set of solar arrays. This is around the point that the ISS had a somewhat unusual appearance due to 2 solar arrays being kept in temporary positions above the middle of the truss structure. By STS-117, the shape we know was better established, with 1 set of large solar arrays now located at either end of the truss. STS-120 delivered the Harmony module, which serves as the connection point for the laboratories of the USA, Europe, and Japan, the latter 2 of which hadn't yet arrived. Another notable aspect of this flight was an EVA repair. When the 4B solar arrays were moved to their permanent position and unfurled again, the crew noticed a tear in a portion of one array. It was left 90% unfurled while a course of action was determined. On flight day 12, the crew performed a rather complex EVA. After manufacturing cufflinks out of existing wires, the Canadarm2 grappled the shuttle's orbital inspection boom as an extension, using it to carry an astronaut out of the solar array on a foot restraint. Unable to view the progress from the station, the astronaut was then backed away to inspect it for himself as the array was slowly deployed the remaining 10%. The operation was entirely successful, and the array was left operating at more or less full power. The next 2 shuttle missions would deliver the European and Japanese laboratories. Well, part of the Japanese laboratory. Columbus, the European laboratory, is an Italian-built cylindrical module not dissimilar from the multipurpose logistics module, and was a simple one-step installation to the Harmony node. The Kibo Japanese module, however, was slightly more complex. It consisted of 3 components: a main laboratory, which was the single largest ISS module, a logistics module fitted on top of the laboratory, and an exposed facility that is manipulated by a small robotic arm. The logistics module arrived first, temporarily berthed to the top of the Harmony module, as it could carry most of the equipment for the laboratory, essentially serving as the lab's moving van. The laboratory arrived next, was berthed to Harmony, and the logistics module was moved into its permanent position. After the final truss and solar array segments were delivered and the Kibo laboratory was configured for use, the exposed facility was attached to the end of it, finally completing the process. However, before this occurred, the Hubble Space Telescope would see its 5th and final servicing mission. STS-125, launched in May of 2009, brought Atlantis to the telescope to bring replacement parts and 2 new instruments, the Cosmic Origin Spectrograph and the Wide Field Camera 3. This mission had a rather unique contingency mission. Because it wouldn't be able to rendezvous with the ISS in the case of an emergency, STS-400 was prepared using Shuttle Endeavour. The 2 orbiters would have rendezvoused with each other at 90-degree angles and used the Canadarm to hold the 2 in place. Using a tether, the crew would have transferred from Atlantis to Endeavour one at a time, along with as much equipment as possible, before Atlantis would be remotely deorbited over the Pacific Ocean. Had this happened, it likely would have ended the program early, as continuing with only 2 orbiters in the fleet would have been near impossible. However, thankfully, STS-125 was a complete success, upgrading Hubble to its most technologically advanced state possible, allowing the telescope to peer deeper into space and therefore deeper into the past to unravel the mysteries of the universe. Of the remaining ISS assembly flights, the most notable is STS-130, delivering the Tranquility module and the cupola. Tranquility holds 6 berthing ports for crew vehicles or stowage, while 1 is permanently occupied by the cupola. Perhaps the most well-known pressurized module, the cupola is both an observatory and a robotics workstation. Its many windows allows the astronauts a clear view of where the robotic arm is, making it easier to operate, as well as providing the most stunning view of the Earth from space that currently exists. With its addition, the ISS was considered 85% complete. The remaining ISS flights were small additions, adding logistics elements, as well as the Russian mini-research module Rassvet on STS-132. This was initially supposed to be the final flight of Atlantis, but NASA was acting behind the scenes to extend the program just a little bit. The NASA Authorization Act of 2010, passed and signed by President Obama in October of 2010, directed NASA to fly 1 additional shuttle mission in 2011 if it could be done safely, primarily to help bridge the gap between the program's end and commercial space programs. SpaceX had yet to get the Dragon spacecraft operating reliably, and Orbital Sciences was still working on their Cygnus cargo spacecraft. So, while Discovery and Endeavour were preparing their final flights, STS-133 and 134 respectively, a plan was made for 1 additional flight. STS-134 had the contingency mission of STS-335 using Atlantis. If this flight wasn't needed, Atlantis would be converted on the spot for one last hurrah, STS-135. Discovery flew her final flight on February 24, 2011.
Booster ignition and the final liftoff of Discovery, a tribute to the dedication, hard work, and pride of America's space shuttle team. The shuttle has cleared the tower.
The single most flown orbiter with 39 flights, she would bring the Leonardo multi-purpose module to the ISS one last time, and this time leave it there as a permanent stowage module. An express logistics carrier, a steel platform for mounting external payloads, was also included, as well as a humanoid robot called Robonaut 2, intended to perform menial tasks around the station. It would operate with moderate success until 2018, when it was returned for repairs and relaunch, but this relaunch has yet to occur. One other unique payload was the SpaceX Dragon Eye sensor, a prototype LiDAR sensor that was tested before being implemented on the Dragon spacecraft itself. This system provided a 3-dimensional image of the space ahead of it, allowing for a precision approach and docking to be performed. After 14 days of work, Discovery landed for the final time on March 9, 2011 at the Kennedy Space Center Shuttle Landing Facility. It was the final daylight shuttle landing, and Discovery was declared officially retired at the point of wheel stop.
Main gear touchdown. The nose of the shuttle being rotated down toward the flight deck. The parachute being deployed. And nose gear touchdown, and the end of a historic journey. And to the ship that has led the way time and time again, we say farewell, Discovery.
STS-134 brought Endeavour on her 25th and final flight on May 16, 2011.
Go for main engine start. 8,
7, 6, 4, 3, 2, 0, and liftoff for the final launch of Endeavour, expanding our knowledge, expanding our lives in space.
Houston, Endeavour, roll program.
Roger, roll, Endeavour.
She brought the alpha magnetic spectrometer, a particle physics experiment to detect antimatter in cosmic rays, which was mounted to a truss segment. She also left the orbiter boom sensor system permanently aboard the station, extending the distance of the Canadarm2. She undocked from the station on flight day 15, bid the station farewell, and landed at KSC 2 days later.
Main gear touchdown. Drag chute deployed by Greg Johnson. Forward gear touchdown. And so after a journey of 6.5 million miles, Endeavour landing in darkness but illuminated by the ingenuity, dedication of every astronaut, scientist, engineer, flight controller, mechanic, and dreamer that helped it fly. The fleet's youngest ship completing its 122 millionth mile after its crew delivered an instrument to the International Space Station that will sift through the cosmic darkness for years to come.
Houston, Endeavour, we'll stop.
The program would have ended here if NASA hadn't gotten their way. However, there was one more mission, one last Hail Mary to the long-standing program.
Okay, Fergie, we're starting to feel pretty good down here on the ground about this one today, so on behalf of the greatest team in the world, good luck to you and your crew on the final flight of this true American icon. And so for the final time, Fergie, Doug, Sandy, and Rex, good luck, Godspeed, and have a little fun up there.
STS-135, the 33rd flight of Atlantis, lifted off on July 8, 2011.
8, 7, 6, 5. All 3 engines up and burning. 2, 1. 0, and liftoff, the final liftoff of Atlantis on the shoulders of the space shuttle. America will continue the dream.
She carried only a 4-person crew in the Raffaello logistics module, though it wouldn't be left on the station. Instead, after transferring supplies to the station, it was filled with unneeded equipment and brought back to Earth. On flight day 11, Raffaello was returned to the shuttle and farewells were made. The station was presented with a US flag flown on STS-1, as well as a small model signed by program officials. Quote, "What you don't see is the signatures of the tens of thousands who rose to orbit with us over the past 30 years, if only in spirit," Commander Chris Ferguson said. The hatch was closed and the shuttle undocked the next day, with flight engineer Ron Guerin ringing the station's bell in the Harmony module.
Atlantis departing the International Space Station for the last time.
The crew took a heap of photos as they moved around the station for about 25 minutes before Atlantis finally departed and headed home. Before it did, the shuttle program released its final payload into orbit, the Pico Satellite Solar Cell Experiment, a small satellite meant to relay the performance of its solar cells back to help shape the design of future solar arrays. Atlantis re-entered the atmosphere from a location where the ISS could watch it happen, allowing for this time-lapse image to be taken, before touching down at the Kennedy Space Center runway 15 on July 21, 2011 at 5:57 a.m. Eastern Standard Time. Mission Commander Rob Navius sounded a little choked up as he declared,
"Having fired the imagination of a generation, a ship like no other, its place in history secured, the space shuttle pulls into port for the last time. Its voyage at an end."
The Space Shuttle program was officially over. More than 20 organizations wanted to display the orbiters in their museums, and months before the final flight was made, NASA announced that the 4 orbiters would be displayed permanently at different locations. The test orbiter Enterprise would be featured at the Intrepid Museum in New York, the trip to which cost her a damaged wingtip when a gust of wind blew the barge carrying her. She officially went on display on July 19th of 2012 inside an enclosure called the Space Shuttle Pavilion. That same year, Hurricane Sandy caused the pressurized enclosure to deflate, collapsing around the orbiter and further damaging her. She was, of course, repaired, and still stands today at the Intrepid Museum, looking brand new. Shuttle Discovery was decommissioned in March of 2011 and put on display at the Udvar-Hazy Center of the Smithsonian. In 2025, 2 Texas senators attempted to pass a provision on a bill to relocate Discovery to Space Center Houston, but the Smithsonian countered that ownership of the shuttle had been transferred to them, and Congress did not have the legal capability to force a transfer. She remains at Udvar-Hazy in a landing state, her payload bay doors closed. Shuttle Endeavour was taken to the California Science Center, temporarily placed in the Samuel Ocean Pavilion. Guests were able to walk around as well as under her, as she had been placed on seismic isolators to protect her from earthquake damage. In 2015, NASA donated the last mission-ready external tank, ET-94, to the Science Center, which was transported from Louisiana in the next year. It was displayed outside the pavilion until 2023, however when Northrop Grumman donated 2 flight-proven solid rocket boosters, a new exhibit was begun. The Samuel Ocean Air and Space Center, currently under construction, will place Endeavour in a launch-ready full stack, as if ready to blast off one final time. Shuttle Atlantis was kept at KSC, displayed at the visitor complex. She sits with her payload bay doors opened and mounted at a 43-degree angle to make it appear as though she's in orbit around the Earth. This way, the 3 orbital shuttles are displayed in their different states: Endeavour in a launch configuration, Atlantis in an orbital configuration, and Discovery in a landing configuration. Other payload hardware was distributed around the country. One Spacelab module is at Bremen Airport in Germany, while the other is behind Discovery at Udvar-Hazy. The Raffaello module was transferred to Axiom Space for reuse in 2023. Around 7,000 thermal tiles were donated to schools and universities around the country, costing the institutions only the amount needed for shipping and handling. 16 of the 42 reusable RS-25 engines have been incorporated into the Space Launch System, unfortunately expended into the ocean for their flights. The remaining engines were donated to various exhibits around the country. The mobile launcher platforms, themselves refurbished from the Apollo program, would again be altered for use in Constellation, then in Artemis, although 2 would eventually be scrapped while 2 all-new ones would be constructed for Artemis, though one was cancelled at 90% completion. The retirement of the shuttle left something of a power vacuum at NASA, while more like a purpose vacuum. As early as the late 1990s, successors to the shuttle were being proposed, such as the Lockheed Martin Venture Star, a single stage-to-orbit spaceplane eventually cancelled due to both cost concerns and difficulty in engineering. NASA had also been developing the Constellation program as of 2005, boasting both a crewed low-orbit vehicle via Ares 1 and a return to the Moon via the larger Ares 5. Utilizing the Orion spacecraft, Constellation would see only one uncrewed test flight, the Ares 1X technology demonstrator, before it was cancelled in 2009. The NASA Authorization Act of 2010 intended to fully revise NASA's future plans and eventually resulted in the Space Launch System and the Artemis program for a lunar return. And Artemis is just... well, it's a whole can of worms. Since the shuttle's retirement, crewed spaceflight continues via the Russian Soyuz spacecraft, as well as the SpaceX Crew Dragon spacecraft, while an uncrewed Dragon variant as well as the Cygnus and Progress spacecrafts continue to resupply the ISS. When Atlantis lifted off for the final time, it was stated that, quote, "On the shoulders of the space shuttle, America will continue the dream." That promise is being fulfilled, just very, very slowly. The space shuttle was an extremely unique vehicle. To date, no other spacecraft is capable of doing all the things that it was capable of. Up to 8 crew, deployment of payloads, return of payloads, on-orbit servicing, and assembly of an entire space station. No other vehicle can do all of these things. However, at the same time, the entire thing was just a mess. Robbed of its initial high concept and high return design, what NASA was left with was a dangerous vehicle too complicated for its own good that likely should have received major upgrades and redesigns throughout its lifetime. It makes absolutely no sense that a spaceplane designed in the 1970s flew all the way until 2011. No other spacecraft outside of the Soyuz has had such a long life. Spaceflight requires constant innovation, and the space shuttle was sort of like stepping onto the bottom step and then staying there for 30 years. By several metrics, the space shuttle was a failure. It never reached the high launch cadence it was born to make. It never made spaceflight into something routine that anybody could do. Even the cost of its reusable nature can be called into question. But boy, it sure did look pretty, didn't it? As usual, there is a lot about the shuttle that isn't in this video. As long as this video is, I kept it as short as I possibly could. If you want some more obscure trivia about the shuttle, I recommend my Shuttle Iceberg video. Aside from that, there are detailed breakdowns of every single mission ever flown, interviews with crew, endless photos and videos, post-flight presentations. There is a wealth of information at your fingertips. I'll leave some helpful links in the description. Thank you for watching, and have a great day.